What if the world had once decided, for reasons written in rock and sky, to turn itself into a frozen memory? That question hangs like a delicate icicle at the edge of human imagination, fragile, clear, and utterly impossible to ignore. The planet that seems so reliably warm on a given summer afternoon, that yields beaches and rainforests and bustling cities, carries in its deep past episodes in which warmth was the exception and ice the rule. Those episodes were not seasons, they were planetary transformations, epochs, when the sun's pale light fell on a world wrapped in white so thoroughly that oceans stilled beneath crusts of ice and continents became great, grinding glaciers. This opening thought is not merely rhetorical. It points to a paradox that sits at the heart of deep time thinking. The climate that appears permanent to a single human lifetime is, on geological timescales, a fleeting state. The present warmth is a brief flare in the grand rhythm of Earth, a rhythm dictated by orbital mechanics, tectonic wanderings, solar evolution, and the slow respiration of the biosphere. The geological record records this rhythm in millimeter-thin layers, in the chemistry of ancient rocks, in the shape of sediments. Buried within those records are moments when Earth's thermostat shifted dramatically, not merely cooler summers or harsher winters, but global reconfiguration. The most famous of those moments belongs to what scientists call the cryogenian, a span 500 million years ago when ice might have clutched the planet from pole to equator. For the listener, imagining a snowball, Earth invites a cascade of sensations, a silence swallowing the scream of the ocean, a hard and crystalline sky, light refracted through endless sheets of frozen water. But beyond sensory evocation, the real mind-bending fact is that such extremes are possible on a planet that also supports warmth and abundance. The same world that wears palm trees today once carried glaciers to the tropics. The machinery of climate is capable of transmutation on scales that dwarf human institutions and memories. This realization is at once humbling and unsettling. It reorders the hierarchy of temporal significance and forces an uneasy question. What does permanence mean on a planet that recycles its face? The evidence for global-scale glaciations is not a matter of musings, but of strata. Geologists find the fingerprints of ancient ice and rock formations, glacial tillites and dropstones, sediments that bear the scars of grinding by glaciers, striations etched into bedrock by the passage of massive ice sheets. There are isotopic shifts recorded in carbonates and in the chemical signatures of oceans that suggest massive changes in ocean chemistry and atmospheric composition. In a few rare places, the deposits of the Neoproterozoic, these signatures align in A. Way, that implies something very large indeed. Ice sheets descending to sea level even in regions now clustered around the equator. That alone would be a striking enough image, yet the implications ripple outward. Where did life hide during these frigid ages? How did the Earth flip back to warmth? And, given such thorough planetary upheavals, what happens to whatever human-like traces might have existed before or during such events? To frame that last question is to open speculative territory, but it is also to engage in a rigorous inquiry. How does the planet preserve its past, and what kinds of past are most easily erased? The processes that bury and destroy also create and reveal. Tectonic collision folds strata into mountains. The mantle swallows the ocean floor. Erosion files once grand structures into sedimentary anonymity. Over tens to hundreds of millions of years, continents migrate, collide, and are shredded. The near-surface geological record is fickle. While some signatures persist for eons, isotopic anomalies, mineralogical oddities, global geochemical shifts, the surface-facing artifacts that stand out to a civilization, such as monumental architecture or manufactured objects, are vulnerable. They can be ground into sand by glaciers, submerged by rising seas, buried beneath successive layers of sediment, or consumed by tectonic recycling. This is where the imagination must reconcile with geophysics. An intense glaciation does more than cover landscapes with white. It mobilizes vast amounts of rock and sediment. It carves and shoves. It scours coastlines and plunges the sea level as water becomes locked in ice sheets. Glaciers are efficient erasers of the shallow record. Cities, if any had once hugged a coastline or river delta, would be subjected to an almost mythic geological indignity. Foundations ripped out, walls reduced to rubble, roofs collapsed, and then ground into glacial flour. The crushed remains would be reworked into new sediments, their chemical traces diluted and dispersed. In areas where ice sheets were thick enough, the crust depressed, and subsequent isostatic rebound would rearrange the topography yet again. Permafrost can preserve organic matter in a suspended time, but over hundreds of thousands to millions of years, even frozen preservation tends to fail. Biochemical degradation, microbial action, and radiative processes slowly dismantle what once seemed imperishable. Yet the planet rarely erases everything completely. There are durable signatures that withstand the metronome of deep time. The composition of sediments can carry anomalous concentrations of metals, synthetic compounds, or isotopic ratios that do not match natural baselines. Chemical scars can be subtle but global, a shift in carbon isotopes indicating massive changes in organic productivity, unusual. Spikes in certain rare earth elements that correlate with industrial-scale extraction and smelting layers enriched with metals. That suggests large-scale metallurgy. Even if a glacier grinds the physical forms into dust, the chemistry of that dust can remain as a whisper in the sedimentary chorus for millions of years. The speculative conversation about erased civilizations pivots on durability versus detectability. If a technologically advanced society had existed millions of years ago, long before humans appeared, what signals might remain? The answer requires a catalogue of what is geologically persistent. Manufactured alloys, for instance, might eventually corrode and recrystallize, but certain metal phases or unusual metal concentrations could leave an imprint. Plastics, the emblem of modernity, are mostly organic polymers vulnerable to oxidation and biodegradation over geologic timescales. They fragment into complex carbon residues and microplastics that migrate through sediments, potentially leaving distinct organic markers in the fossil record. Radioisotopes produced by nuclear activities would leave isotopic anomalies that, under the right conditions, could be exceptionally diagnostic. Yet even these markers can be scattered or buried. Their detectability, a function not only of abundance, but of the vagaries of deposition and preservation. Beyond chemistry, there are structural records that survive surprisingly well. Geological formations built by life, stromatolites, reefs, can persist and tell of ecosystems that survived cataclysms. Mass extinctions, when they occur, are recorded as abrupt shifts in fossil assemblages and geochemical proxies. A civilization's collapse on a planetary scale might be detectable not because objects remain unweathered, but because global. Systems are left rattled. Sudden alterations in sedimentation rates, shifts in greenhouse gas proxies, anomalous extinction patterns. These are the subtler clues that a speculative investigator must pursue. They are not the ruins of columns nor the rusted skeletons of machines. They are changes in the rhythm of Earth's heartbeat. There is a philosophical weight to this inquiry. To entertain the possibility of bygone civilizations is also to confront the transience of human achievement. Human-made things, skyscrapers, satellites, entire urban mosaics, may be majestic to the eye, but are geologically ephemeral. The memories of human societies are etched in stories, archives, and physical artifacts. The planet, however, keeps a different ledger, layers of sediment and isotopic ratios in the archive of fossils. The two ledgers speak different languages. The documentary mind, drawing from the scientific ledger, considers what a future geologist might read and what it would take for a human observer to reconstruct a vanished technological activity from only a handful of anomalous chemical signatures and disturbed strata. That existential lens sharpens when the present-day climate conversation is parked beside the deep past. It is ironically instructive that the process is now being driven by human activity. Changes in greenhouse gas concentrations, rapid warming, ocean acidification are of a kind that can imprint themselves upon the geological record. In the distant future, should humans vanish, the fingerprints of the Anthropocene might be observable as a thin, globally synchronous layer, a sudden perturbation in isotopes, a surge of synthetic particles, a spike in certain metals. Conversely, the deep freeze of a snowball, Earth would leave an arresting stratigraphic sequence. Glacial deposits at tropical latitudes, a hiatus in carbonate deposition, chemical excursions associated with the subsequent recovery, and greenhouse episodes. Each climatic extreme leaves a different sort of fossilized book to be read by those with the patience and instruments to translate it. The emotional quality of this thought experiment, the sense of being small and temporary, is not merely melancholic. It can be a source of wonder. To contemplate a world that has undergone such extremes is to appreciate the resilience and adaptability of life, which has persisted through repeated rehearsals of disaster and recovery. It is also to perceive the precariousness of the human present. The contemporary warmth is framed not as an absolute triumph, but as a transient chapter in an ongoing planetary narrative. This reframing can instill humility, human concerns, important as they are on the day-to-day scale. are nested within a backdrop of processes that operate on timescales both immense and indifferent. If the question at the outset, could ice have erased entire civilizations, seems to tilt towards sensationalism, the documentary stance insists on a measured curiosity. It treats the possibility not as a premise to be accepted, but as a lens through which to examine the durability of different kinds of evidence. That stance is methodical. It asks what signatures might survive, how they would be recorded, and how they might be distinguished from natural variations. The search therefore becomes not a hunt for ruined temples beneath the ice, but a precise interrogation of the geological and chemical record, isotopic anomalies, sedimentological oddities, and fossil assemblages that do not fit expected patterns. At the same time, the speculative documentary voice must hold space for the psychological torque that such ideas exert. There is a distinct quality of awe in realizing that Earth's history contains chapters so alien that a human mind, accustomed to decades, struggles to comprehend them. The narrative voice takes care to translate scale into emotion without lapsing into melodrama. It asks the listener to feel the smallness of a single life without flattening it into despair. It invites curiosity, the scholarly kind that begins with data and then allows the imagination to extend cautiously beyond it. Ultimately, this opening exploration is a meditation on erasure and persistence. Ice is both destructor and preserver. It grinds and buries, yet in some circumstances it conserves. Glaciation reshapes landscapes, but it can also slow chemical weathering in ways that preserve certain records. Plate tectonics consumes the crust but creates mountain ranges that expose deep records. Life interacts with these geophysical forces, sometimes amplifying changes and sometimes cushioning them. The interplay between biosphere and geosphere is the theater in which questions of erasure and remembrance are played out. This first segment closes not with answers but with a clarified curiosity. It promises that subsequent inquiry will move from broad reflection to detail, from the image of the planet wrapped in ice to a systematic presentation of mechanisms, evidence, and the kinds of traces that survive deep time. The next part will delve into the science that reconstructs ancient climates, into the ways sediment and isotope act as proxies for vanished states, and into the speculative frameworks that ask how a civilization, if it ever existed before the human chapter, might be visible to a patient geologist. For now, the listener is left with a stark, almost cinematic thought. The Earth is older than memory, and its seasons include transformations so vast that warmth itself can be only a temporary favor. In that humility lies the true prompt for exploration, to read the rock record closely, to listen for chemical whispers, and to acknowledge that the planet's archive is both vast and partial, and that the stories it preserves are those that have endured, not those that were merely loud. What if the planet's calendar were not written in years, but in millennia, in subtle bends and wobbles of an orbit traced around the sun? That quiet image is the hinge of the next question when ice returns. Will humanity be prepared for an epoch written not by short-term weather, but by the slow arithmetic of celestial mechanics and the compounded reactions of oceans, rocks, and air? The long story of ice has a clock. It does not tick like the second hand of a watch. It breathes on scales so broad that entire human civilizations are but brief pulses between ticks. That clock is most clearly expressed in what scientists call the Milankovitch cycles, the trio of slow, predictable variations in Earth's motion around the sun. Individually, each cycle is modest, a slight elongation of orbit here, a small tilt of the planet's axis there, a gradual procession of the seasons. Together, they orchestrate the distribution of sunlight over latitudes and seasons, and through that distribution they nudge the climate into states that can persist for tens of thousands of years. First, there is eccentricity, the shape of Earth's orbit, which waxes and wanes between near circular and slightly elliptical on cycles of roughly 100,000 and 413,000 years. When the orbit is more elliptical, the distance between Earth and Sun changes a little more across a year, altering the seasonal intensity of sunlight. The change in total energy is only a fraction of a percent, yet the pattern of its delivery across seasons matters greatly for whether winter snow survives a summer. Second is obliquity, the tilt of Earth's axis relative to the plane of its orbit. This tilt varies between about 22.1 and 24, 5 degrees on a roughly 41,000-year rhythm. Tilt governs the contrast between seasons. A higher tilt amplifies summer warmth in the high latitudes, making it harder for snow and ice to endure. A lower tilt softens seasonal extremes and allows winter accumulation to persist. The slow drifting of this angle silently changes the planet's seasonal mood. Third is precession, the wobble of Earth's axis, much like a spinning top that slowly traces a circle. Precession shifts the timing of the seasons with respect to perihelion and aphelion, the points of closest and farthest approach to the sun, on cycles of about 19,000 to 23,000 years. In concert with eccentricity, precession modulates which hemisphere experiences stronger summers and which shoulders the milder ones. Milankovitch himself calculated that these orbital variations change the pattern of incoming solar radiation. Insolation! More! Strongly at some latitudes than others. The crucial arena for glaciation is the high-latitude summer. If summers there are cool enough that winter snow does not fully melt, the snow accumulates over successive years and the ice sheet begins its slow ascent. That accumulation alters the surface reflectivity, albedo, of those regions. White ice reflects more sunlight than dark ocean or soil, and so a modest initial cooling can snowball into much larger ones. The ice albedo feedback is the amplifier that transforms small orbital nudges into continental-scale glaciation. But the Milankovitch clock is not the whole story. It is a metronome that sets the tempo to which other processes compose. The climate system is a network of amplifiers and dampers, oceans that store heat and carbon, the atmosphere that shuttles greenhouse gases, mountains that bind carbon through rock, weathering, volcanoes that jettison both cooling aerosols and warming carbon dioxide. The transition from a cool century to a full-blown ice age is mediated by these agents. Consider carbon dioxide, the subtle lever of Earth's thermostat. Atmospheric CO2 does not merely respond passively to temperature, it participates actively. When oceans cool, their ability to hold dissolved gases increases, drawing down atmospheric CO2. Biological pumps, the sinks of organic carbon accomplished by phytoplankton and the burial of their remains, can intensify, aided by changes in nutrient supply and ocean stratification. Conversely, when the ocean overturning weakens and dead zones expand, CO2 can accumulate in the atmosphere. Thus, orbital-induced changes in insolation can set in motion oceanic and biological processes that amplify cooling or warming over millennia. Plate tectonics, moving at the pace of fingernail growth, quietly composes the long-term stage on which glaciations play. The position of continents influences the climate through albedo and ocean circulation. When large landmasses sit near the poles, they offer a platform for ice sheets to grow outward. Mountain building uplifts fresh rock, which weathers chemically when exposed to rain and rivers. The weathering of silicate rocks consumes atmospheric CO2 and precipitates long-term cooling. A new mountain range, carved over millions of years, can nudge atmospheric chemistry enough to predispose the planet toward glaciation. Likewise, the opening or closing of ocean gateways, channels between basins, redirects ocean currents, altering heat transport from equator to poles. The rearrangement of continents over geological time is not an incidental detail. It is a slow architectural shift that reshapes the climate's baseline. Volcanoes, too, play double roles. Large eruptions inject sulfate aerosols into the stratosphere, reflecting sunlight and creating ephemeral coolings that last a few years. But over tens of thousands of years, volcanic outgassing replenishes atmospheric CO2, adding a warming tendency. The net effect depends on rates of eruption, the size of continental sinks, and the interplay with weathering. In some narratives of deep time, episodes of enhanced volcanism have both triggered brief cold spells and later contributed to greenhouse-driven recoveries. Glacial inception is a story of thresholds and hysteresis. Ice sheets grow slowly. They also forget slowly. Once a continental ice mass reaches a certain size, its elevated surface sits in colder air. Higher altitude leads to more snowfall and less melt. The mass of the ice load depresses the crust, changing local sea levels and drainage patterns. These are structural alterations that favor persistence. To reverse such a state requires not just a return to previous orbital configurations, but additional warming capable of overcoming the albedo and elevation feedbacks. The climate thus displays memory. It can be driven into a glacial rhythm and remain there through orbital variations that might otherwise suggest a return to warmth. The mechanics of the ice itself are not poetic abstractions, but powerful physical processes. Snow that survives summer compacts into firn, then metamorphoses into glacial ice under its own weight. The ice does not sit inert, it flows. Under gravity and pressure, glaciers behave as rivers of ice, sliding, deforming, and carving. Basal sliding, where meltwater lubricates the interface between ice and rock, can accelerate movement, leading to pulses and surges. The glaciers grind bedrock into fine powder, glacial flour, and carve U-shaped valleys and striations that become the fingerprints of past ice. This erosive appetite redistributes sediments, buries former landscapes, and reconstructs coastlines, altering the very templates of future climates and ecosystems. There is a particular mystery in the recent geological past. Why did the dominant rhythm of the last million years settle into a roughly 100,000-year cycle? Orbital eccentricity's direct effect is slight, yet quaternary glacial interglacial variations adhered to a rhythm aligned with eccentricity for the last 800,000 years, even though earlier the 41,000-year obliquity cycle was more dominant. This 100,000-year problem invites explanations that combine orbital forcing with internal feedbacks, the interplay of ice sheet dynamics, bedrock properties, and greenhouse gas concentrations may have conspired to lengthen glacial intervals. Some hypotheses suggest that the removal of regolith, soft sediments stripped from continental surfaces, changed the way ice sheets interact with their beds, producing larger, more stable ice sheets with slower cycles. Others point to slow geochemical processes or to the role of stochastic events, volcanic, oceanic, or atmospheric, that, layered upon the orbital beat, produce a complex, emergent rhythm. Beyond these mechanisms, the cryosphere interacts in surprising ways with dust and life. Wind-blown dust darkens ice surfaces, lowering albedo and promoting melt in certain settings, yet the same dust, when deposited into iron-starved ocean regions, can fertilize phytoplankton and accelerate carbon drawdown. Microbial life within snow and ice. The cryobiome can influence melting through pigments and metabolic heat. The biosphere, for all its fragility in the face of towering ice sheets, also participates in the planetary balancing act, nudging atmosphere and ocean chemistry over millennial spans. If the thought of ice returning prompts anxiety, the timescale is an immediate caveat. Milankovitch cycles and tectonic shifts unfold over thousands to millions of years. Yet this is not a comfort so much as a warning. The thresholds that distinguish a warm interglacial from a full glacial are not always crossed in a smooth, gradual way. Rapid reorganizations can occur when feedbacks align with an external nudge. A freshwater influx to the North Atlantic from melting ice, for example, can choke off the Atlantic meridional overturning circulation, rapidly cooling northern hemisphere regions. The climate system is replete with tipping points where a relatively modest perturbation cascades into pronounced change. What then of humanity, of cities, of agriculture, of the cultural scaffolding that has flourished in the recent warm epoch? The answer is not a single script. The human story is plastic and contingent. On the one hand, human technologies and institutions can buffer and adapt to a broad range of environmental changes. Irrigation. Networks can redistribute water, energy systems can heat and cool, and migration can track shifting habitable zones. On the other hand, the inertia of global systems, food production, supply chains, densely populated coastal regions, is sensitive to even moderate climatic reorganizations. An ice-advancing world would not be a sudden cinematic freeze, but a staggered series of stresses. Shortened growing seasons at high latitudes, pressure on water resources in mid-latitudes, displacement of coastal populations as sea levels respond to ice distribution elsewhere, and geopolitical strains as communities scramble to secure arable land and energy. There is a peculiar psychological dimension to these scenarios. Humans are geared to respond to fires that burn fast and enemies that arrive on a timetable measured in months or years. Millennial-scale processes test a different kind of governance and imagination, long-term stewardship, institutional memory stretching beyond electoral cycles, infrastructural investments designed for climates that will not exist in a few centuries. The very act of planning on the timescale of orbital mechanics is a strange exercise in humility and daring. It asks societies to build resilient systems that can be maintained across generations, to preserve knowledge when institutions wobble, and to fold scientific foresight into cultural practices. The slow dance of ice and warmth is not merely an academic spectacle, it is the framework within which human contingency is cast. To see Earth's climate through the lens of Milankovitch cycles and their compasses is to perceive a planet capable of dramatic, patient transformation. It is to understand that ice is not an invader, but a possible configuration of a dynamic system. That glaciations rise and fall as parts of the planet's long metabolic rhythms. That recognition reorients urgency. Long-term thinking does not displace immediate responsibility. If orbital mechanics sets the tempo, human actions alter the amplitude of the response. Greenhouse gas concentrations, land use changes, and aerosol emissions can all modulate the climate sensitivity to orbital forcing. The Anthropocene, even if fleeting on geological timescales, has the potential to superimpose a sharp, global-scale perturbation upon the natural beat of Ice Age cycles. In that intersection lies both risk and an opportunity for agency. The choices made now will change the context within which the planet's slow cycles will continue to operate. As part two of this reflective documentary arc closes, the listener is left with a dual impression. On one level, the mechanics are patiently physical, a clock of celestial motion, amplifiers in ice and ocean, geological actors that shape atmospheric chemistry. On another level, the implications are existential. The knowledge that Earth's climate has a deep time choreography makes human tenure appear both precarious and potent. The formation of ice ages is not a spectacle removed from human affairs. It is a process that, given enough time and a confluence of amplifiers, can recast the templates of civilization. The next segment will turn its lens from mechanism to archive, how and where the planet keeps the record of these great swings, and how those records might hide or reveal traces of a world that once cooled profoundly. For now, the essential takeaway is simple and unsettling: the slow arithmetic of astronomy and the patient responses of oceans. Ice and rock can together drive humanity's climate into configurations that feel, in human terms, radical, and that the capacity to notice, to plan, and to adapt must extend beyond a lifespan into the longue durée of planetary rhythms. What if the planet once decided, in a manner so thorough it rewrote coastlines and chemistry, to seal itself in a frozen envelope, not for a season, but for millions of years? That question hangs in the scientific imagination like a bell whose tone is both gorgeous and dreadful. It is the nucleus of the snowball Earth hypothesis, a claim that during the Neoproterozoic, hundreds of millions of years before animals with skeletons swam in Cambrian seas, ice advanced so far that the world's oceans, at least at the surface, were choked with white. The idea is simple to state and impossible to hold without shivering. A planet whose tropics gleamed with glaciers, whose seas were capped by a shell of crystalline silence, whose sunlight struck surfaces that reflected nearly all of it away. The evidence for such an audacious state arrives in geological fragments that, together, form an argument. In sediments laid down 5, 6, 700 million years ago, geologists find rocks that could only have formed when ice met shallow seas, diamectites, coarse, unsorted deposits, sometimes called tillites, that bear the signature of ice-rafted debris. Dropstones, pebbles, and cobbles unnaturally perched within otherwise fine marine muds testify to icebergs that ferried Earth's interior continents into ocean basins. Striations etched into bedrock, the linear scars of moving ice, show that glacial grinding reached latitudes that, when their original orientations are reconstructed using paleomagnetism, correspond to regions that ought to have been tropical. Above some of these glacial piles lie strange, abrupt layers of carbonate rock, carbonates, whose chemistry and rapid precipitation hint at an ocean recovering from an extreme chemical and temperature shock. And wrapped through these sediments are isotopic anomalies, swings in carbon stable. Isotopes that suggest profound reorganizations of the global carbon cycle. Individually, each of these traces could be explained by local or regional events. Together, in their global alignment and in the paleolatitude evidence, they form a pattern that is difficult to dismiss. The most dramatic interpretation, the hard snowball model, suggests nearly complete ice cover, sea ice extending to the equator, a world in which the sunlight that reached the surface was reflected back into space, and the surface ocean isolated from the atmosphere and from sunlight-driven productivity. An alternative, less absolute model, the slush ball. Earth imagines persistent open water in tropical belts or polynyas, patches of liquid ocean that allowed continued photosynthesis and exchange with the atmosphere. The debate between these images is more than academic. It probes the very limits of habitability and of Earth's resilience. How does a planet flip into such a state? The opening of the narrative requires a modest nudge and powerful feedbacks. A common sequence begins with a cooling, perhaps driven by a decrease in atmospheric carbon dioxide, a changing continental configuration that increases albedo or disrupts ocean currents, or an uptick in reflective aerosols. Where that nudge is small, local processes can amplify it. Snow that survives a summer does not vanish. It accumulates, compacts, and increases surface reflectivity. White ice throws sunlight away. The more area the ice claims, the more solar energy is rejected, and the more the planet cools. This ice albedo feedback can transform incremental changes into planetary scale reconfiguration. The same physics that thins a winter's comfort into a year of hardship is capable, on longer time scales, of knitting a world into an ice shell. Even as ice spreads, the engine room of recovery is quietly active beneath the frozen face. Volcanic outgassing does not stop because continents are covered. Carbon dioxide continues to invade the atmosphere from mid-ocean ridges and volcanic arcs. But with global silicate weathering, the chemical process by which rain erodes rock and locks carbon into carbonate minerals, dramatically slowed by cold and ice cover, the atmosphere becomes a one-way sink for volcanic CO2. Over the course of millions of years, carbon accumulates. The greenhouse effect amplifies. Eventually, the atmospheric concentration of CO2 may have risen to thousands of parts per million, producing a greenhouse strong enough to break the ice. When that thaw begins, it does so catastrophically. Ice collapses, albedo plummets, and the ocean system breathes out in a great, rapid chemical upheaval. The capped carbonates are the sedimentary echo of that moment, layers of carbonate precipitated swiftly as the ocean chemistry, loaded with dissolved ions and supersaturated in many places, settled into a new equilibrium. That rebound bears an emotional paradox. On one hand, the idea of CO2 is both culprit and savior, the slow villain whose accumulation eventually frees the planet from its frozen prison is almost poetic. On the other, it underscores the nonlinearity of planetary systems. The very processes that can push a planet toward an inhospitable state also furnish the means of escape. The snowball thus reads like a book that narrates both doom and deliverance, an epoch of constraint followed by an interval of explosive change. What did life do during these long winters? The fossil record around the cryogenian interval is sparse, a lacuna that amplifies the mystery. Microbial communities, however, are robust. The slush ball model offers refuges, equatorial polynyas where light persisted, thin leads in the sea ice that allowed photosynthesis, and hydrothermal vents on the ocean floor where chemosynthetic ecosystems could persist in the dark. Even in harsher interpretations, life need not have been entirely extinguished. Microbial mats and hardy eukaryotes could survive in isolated pockets. Spores and cysts could wait for better times. The reduction in habitable area might have imposed severe genetic bottlenecks, pruning diversity and setting the stage for later evolutionary radiations. It's no accident that after the last of the cryogenian glaciations, the fossil record awakens with a striking flourish. The Ediacaran and then the Cambrian are chapters in which multicellular life diversifies and experiments with new body plans. Where the snowball Earth was a crucible that forced innovation by truncating competition, or merely one of many preconditions that allowed complexity to flourish, remains an open and intensely debated question. The geological consequences of such deep freezes were also profound. Ice is an agent of abrasion and burial. Glaciers carve valleys, grind bedrock into silt and sand, and transport enormous masses of detritus across continental shelves. Where ice meets ocean, it can scour and rearrange the shallow seismic architecture of coasts, piling till and smothering previous sedimentary records. In those places, any fragile traces of prior surface conditions, soil horizons, delicate biomineralized structures, or even structural artifacts, if one extends speculation to pre-human technologic eras, would have been subject to pulverization and burial. The cryosphere is a ruthless archivist. It hides as it writes, compressing the past into stony anonymity. Yet the planet is not without watchdogs. Chemical signatures persist where physical shapes are obliterated. Global isotopic excursions in carbon, sulfur, and other elements are hard to erase. The shift in C values across cryogenian stratigraphy points to global disruptions in the carbon cycle, periods when organic carbon burial and the balance of methane and carbon dioxide change dramatically. Similarly, layers enriched in certain metal concentrations or bearing unusual mineral assemblages can be persistent fingerprints, long after shapes have been ground to dust. These are the whispers that a patient geologist listens to, anomalies that cannot be explained by ordinary sedimentary processes, synchronous changes recorded at distant localities, and abrupt transitions from glacial to non-glacial depositional environments. The Snowball Earth episodes turn the prior reflection about erasure and persistence into a case study. If a technological civilization had arisen prior to or during such a glaciation, what would survive? The immediate answer, drawn from the mechanics of ice and stratal burial, is not encouraging. Surface constructions would be vulnerable, foundations crushed, coastal complexes submerged, and manufactured landscapes ground into sediment. The chemical residue, however, could be different. Massive extraction and smelting, leave traceable signatures, anomalous metal concentrations, isotopic skewing from industrial processes, residues of organics transformed into refractory molecular fossils. Nuclear activity, had it existed, would leave radiogenic fingerprints in isotope ratios that decay on timescales longer than most. Organic molecules survive. While snowball conditions would shuffle and dilute these signals, they may yet linger as faint, global markers that trouble the chemist's instruments. One of the more uncanny outcomes of this history is the interplay between catastrophe and innovation. The cryogenian freeze, however absolute, was followed by one of the most fecund intervals of biological novelty. The release from ice may have fostered nutrient surges, freshly ground rock laden with weathered minerals washing into oceans, fertilizing blooms of microbial life and setting off cascades of biological productivity. Those rebounds, when coupled with the isolation and selection pressures of the preceding cold, could have produced the conditions for complexity to expand. There is a narrative symmetry in this. The planet's punishment contains the conditions of its recovery. The mood one carries from these facts is a mix of humility and urgency. Snowball, Earth, speaks to the power of planetary feedbacks and the unpredictability of thresholds. It shows that the Earth system can oscillate to extremes that feel, to human sensibilities, apocalyptic. And yet those extremes are episodes in a long, indifferent geological biography that includes both obliteration and renewal. The episodes draw attention to the scale mismatch between human affairs and planetary mechanics. Millennia of ice accumulation and removal dwarf human institutions, yet because humans now alter greenhouse gas inventories on geological timescales, the human impact becomes entangled with mechanisms that once drove ancient glaciations. The image of carbon as both a slow valve and a quick agent of change gains a new poignancy. For an observer translating this deep-time narrative into present-day implication, the lesson is twofold. First, resilient systems emerge less from invincibility than from diversity of strategy, refugia, mobility, and the preservation of knowledge across crises. Second, the Earth's archive insists that some traces are harder to erase than others. Physical monuments are ephemeral in the face of continental ice and tectonic recycling. Chemical signals, however, can echo for hundreds of millions of years. That difference shapes how the past is read and how plausible speculations about pre-human techno-signatures must be judged. As this segment closes, the snowball Earth hypothesis stands as both a geological proposal and a philosophical prompt. It forces the listener to reconcile the apparent permanence of everyday warmth with the reality that climate can swing into. Extremes that remap possibility itself. It reframes the planetary story as one of cycles and thresholds, of freezes that both obliterate and set the stage for innovation. In the quiet aftermath of these ancient snows, life, stubborn, adaptable, inventive, found paths to persist and to diversify. The record it left is incomplete, scored by the harshness of ice and the patience of chemical memory. The next chapters of the documentary will turn toward those records, the capstones and anomalies, the mineral whispers and fossil gestures that together let the planet tell its own autobiography. For now, the image lingers of a world that dared to freeze and then dared more abruptly to thaw, a global heartbeat that once beat in crystalline time. What if the last time Earth felt like a different planet was not a single icy episode long ago, but an entire geological chapter that shaped the map of continents, the patterns of rivers, and the trajectories of life? That is the question hovering over the Pleistocene, the most recent great ice age, a vast interval stretching from roughly 5 million years ago to about 11,700 years before the present. On the scale of human history, it is a remote preface. On the scale of geology, it is the scaffolding of the modern world. To read it is to read the planet's recent handwriting, cycles of advance and retreat, abrupt pulses and long slumbers, erosive violence and hush-preserving cold. The Pleistocene is not a single cold breath, but a choreography of many. Glacial and interglacial cycles pulsed across the epoch, their rhythms set by the same celestial mechanics already introduced, the Milankovitch cycles, yet modulated by oceans, ice sheets, ears, greenhouse gases, and chance. For most of those 5 million years, ice did not simply sit at the poles. It marched, like a slow tectonic predator, over high latitudes and across continents, the Laurentide ice sheet in North America, the Fennoscandian and British ice storms in Europe, the Patagonian ice fields in the south. Mountains hosted colossal valley glaciers. Sea level, obedient to the mass of frozen water, rose and fell by scores of meters with each expansion and demise of the great sheets. These were not gentle oscillations, they were rearrangements of habitable space. The traces of those rearrangements are meticulous in the geological ledger. Where ice ground the bedrock, it left striations and polished surfaces, linear scars that tell a story of direction and force. Moraines marked the stopping lines of ice. Drumlin and Esker sketched the flow of meltwater beneath, frozen, then worn smooth. In coastal basins, the Pleistocene's signature is written as steep terraces and submerged shorelines, the planet's memory of times when sea level could be 120 meters lower than today. In ocean sediments, the retreat and return of ice are encoded in shells of foraminifera and in the ratio of oxygen isotopes 0.18016, a subtle meter that records global changes in ice volume and ocean temperature. Ice cores, the very heartbeats of the youngest glaciations, hold trapped bubbles of ancient air, concise chronicles of CO2 and methane, of dust content and volcanic ash, all stacked like pages of climate narrative. Yet the Pleistocene was more than a slow metronome. It was punctuated by abrupt events that read like cliffhangers in Earth's story. The ice didn't always retreat in a steady thaw. Sometimes the world yawned open in rapid warmings. Dansgaard, Oeschger events, recorded in Greenland ice cores, and sometimes it slammed cold again within decades. Heinrich events sent armadas of icebergs into the North Atlantic, spilling fresh water and sediment across ocean basins. Their fallout can be seen as bands of pebble-rich layers in marine cores, testimony to massive surges of ice discharge. These disruptions could choke ocean circulation and produce regional cooling, even as other parts of the globe warmed. The younger Dryas, a late glacial return to cold, felt like a planetary hiccup, a stubborn reversal that delayed the full entry into the Holocene until a final thaw smoothed the world into its modern patterns. The consequences for life were profound and varied. Ecosystems shifted geographically, not merely in composition. Forests withdrew and expanded with the ice's lunge. Grasslands and the uniquely named Mammoth Steppe, a vast, cold, temperate grassland stretching across Beringia and Siberia, became the lungs of a world that supported megafauna. Woolly mammoths, steppe bison, giant ground sloths, and other behemoths roamed expanses that would now be ocean floor or temperate forest. In some regions, glaciation produced refugia, patches of land spared the worst of the ice's fury. Islands of relative stability where species clung on and evolved in isolation. Pollen preserved in lake sediments traces the slow choreography of vegetation, pine and spruce advancing in the cold, deciduous trees retreating, tundra grasses opening wide as ice came. The biological impacts were not only geographic but genetic. Populations fragmented and converged in response to advancing ice and falling seas, producing bottlenecks and radiations. The genetic signatures of many modern species carry the memory of those contractions and expansions. Alleles that survive in refugia now spread as warming allowed dispersal. That pattern is one reason the Pleistocene matters to modern biodiversity, because the ecological templates of today were sculpted in that cycle of loss and return. For humans, late arrivals on the scene, the Pleistocene was a crucible. The archaeological record shows that hominin populations moved with the shifting climate, tracking resources and colonizing new landscapes as ice retreated. Coastlines that once provided rich foraging zones were reconfigured as sea level rose after the last glacial maximum, drowning now submerged shelves that may yet hold faint human stories. Permafrost and peat in some places conservatively preserved organistic artifacts and DNA. In others, the grinding of ice and river work erased the faintest traces. The Pleistocene's environmental drama shaped migration corridors, isolated populations, and influenced the subsistence strategies that set the stage for agriculture and settled life in the subsequent Holocene. Yet, the epoch's role as a maker or breaker of cultural complexity is not a simplistic causal chain. It is a palette of stressors and opportunities that molded human adaptability. From a geomorphological standpoint, ice is both a sculptor and a conveyor. The grinding teeth of glaciers pulverized bedrock into silt and sand. This glacial flour, transported by meltwater, enriched marine and terrestrial systems with minerals, changed sedimentation patterns, and in some cases increased primary productivity. Proglacial lakes formed as ice-dammed valleys, storing vast reservoirs of fresh water. When those dams failed, as in the colossal draining of Lake Agassiz, the consequences could be global. Sudden influxes of fresh water into the North Atlantic modified thermohaline circulation, possibly triggering stadials, and their meltwater pulses raised sea level tens of meters in geologically brief intervals. Such pulses reconfigured coastal biomes and human habitation alike, converting formerly fertile plains into new seascapes. The Pleistocene is also a study in preservation and erasure. In some contexts, cold preserved life in exquisite detail. Permafrost has yielded frozen carcasses with intact fur, stomach contents, and sometimes DNA. Peat bogs have held pollen and plant macrofossils with astonishing clarity. In other contexts, the very power of ice to move was erasure incarnate. Urban scale disturbances by glacial action could obliterate earlier landscapes, burying soils and killing off local ecosystems. The repeated scraping and deposition in formerly glaciated regions means that much of the surface record before the Pleistocene was reworked. For any hypothetical ancient technosignature, an engineered structure, or synthetic residue, Pleistocene processes would act as a sieve. Some chemical markers might be dispersed and diluted, others physically ground away, and still others trapped and preserved in protected sedimentary pockets. At the chemical level, the Pleistocene's fingerprint is also unavoidably clear. Ice core gas bubbles reveal a compelling correlation. Lower CO2 and CH4 during glacials, higher during interglacials. The swings in greenhouse gas concentration are not merely correlative, they are mechanistically tied to ocean circulation, biological productivity, and the carbon sequestration processes that vary with climate state. Dust content in ice cores increases during cold, dry glacial periods, a symptom of windier conditions and expanded aridity in continental interiors. These chemical records provide a temporal resolution unmatched by many other archives, allowing modern science to read abrupt events and correlate them to marine and terrestrial signals. Within that chemical record are the echoes of rapidity, events that occur on human timescales but are embedded in geological narratives. The abrupt warming events recorded in Greenland happened in a matter of decades. The planetary climate system, though generally slow, admits of thresholds where feedbacks align and produce fast transitions. For societies, the implication is unsettling. Change need not be glacial to be swift. The Pleistocene also left a legacy in the planet's physical arrangement. At the last glacial maximum, roughly 21,000 years ago, the continents wore an altered physiognomy. The southern edge of ice pushed into what are now the northern United States and northern Europe. Sea levels were low enough that Beringia connected Asia and North America. Coastlines were several miles seaward of today's shores. That rearrangement enabled biotic exchanges and human migrations that would have been impossible otherwise. The thaw returned sea levels, inundated coastal plains, and sculpted the hypsometry of continents into forms familiar now. Isostatic rebound, the gradual rise of land after the relief of ice weight, continues to this day in formerly glaciated regions, subtly changing shorelines and influencing earthquake patterns. One cannot describe the Pleistocene purely in terms of physical processes without attending to its psychological echo. For the modern observer, the epoch instills a particular type of humility, the recognition that landscapes now taken for granted, plains where cities stand, continental shelves that were once human playgrounds, are transitory arrangements. The Pleistocene cycles remind that the environment of human civilization is not static, that species and ecosystems have repeatedly reorganized around climate beats, and that the modern configuration is the latest act in a long-running drama. This recognition can be sobering. It suggests that stability is a gift, not a guarantee. When the Pleistocene finally yielded to the Holocene, the world did not simply warm and stop. The transition was messy, spatially heterogeneous, and punctuated by instability. Patterns of extinction in the late Pleistocene, particularly of megafauna in many regions, are debated and complex. Climatic stresses, human hunting, habitat fragmentation, and combined pressures likely played parts in different places. The end of Ice Age extinctions are not one story, but a chorus of regional collapses and survivals, each with its own actors and causes. Yet the result was unmistakable. The composition of large vertebrate communities shifted, and in many regions the iron grip of the Pleistocene's cold-adapted ecosystems loosened, allowing other trajectories to proceed. One of the enduring lessons from studying the Pleistocene is the importance of timescale perspective. Processes that seem slow when viewed through the span of a human life, glacial growth, mountain uplift, can nonetheless produce outcomes that, from a generational standpoint, are dramatic. Coastlines recede, rivers reroute, forests collapse. Conversely, some events within the Pleistocene were sudden and could have overwhelmed societies with little warning. This dual character, slow backdrop with episodic abruptness, is what makes the epoch particularly relevant when considering contemporary change. The planet's capacity for reorganization is both a distant memory and a present possibility. From the vantage of a speculative documentary, the Pleistocene functions as a case study in how a planet negotiates extremes and records them. Its sediments, ice cores, and geomorphic forms are archives that encode information about temperature, atmospheric chemistry, sea level, and ecological distribution. They are also archives of erasure. Many surfaces were scoured clean, many sediments remobilized. For any inquiry into deep time legacies, the Pleistocene is a reminder of the duality of preservation and oblivion. As the Pleistocene recedes into the conceptual backdrop, it leaves the listener with several impressions. First, that the most recent ice age was not a singular event, but a long, rhythmical chapter with episodic fits, an ensemble of processes that together shaped modernity's stage. Second, that the epoch's physical and chemical records provide both fine-grained and long-term evidence of how climates can reorganize. Third, that life, flora, fauna, and humans responded with both vulnerability and ingenuity, moving, adapting, fragmenting, and radiating across the shifting mosaics of habitat. Finally, the Pleistocene suggests a moral. The environment humans inhabit is contingent, forged by cycles that operate beyond a single lifetime and yet susceptible to abrupt shocks that have real human consequences. In the chapters to come, the narrative will approach the Pleistocene's details with tools of geology, paleoecology, and climate science. The oxygen isotope curves, the story of the Laurentide ice dome, the genetic fingerprints of refugia, the mechanics of meltwater pulses. It will keep returning to the question of what the planet chooses to remember and what it consigns to dust. For now, the epoch hangs as a stark reminder. Ice is not merely a relic of an earlier age, it has been a dominant sculptor of the modern world, its rhythms braided into the rivers, the soils, the species distributions, and the hidden fingerprints of the air we breathe. What does it mean, in the register of planetary drama, for entire continents to become instruments of cold? That image, Europe and North America draped beneath ice kilometers thick, is not a theatrical exaggeration. It is a literal description of a mood the earth has assumed many times, an era when landscapes familiar to the living were remade into an architecture of white and stone. To imagine that architecture is to imagine force, a slow sculpture, not a single thunderbolt of change, but a long, grinding choreography in which ice is both artist and eraser. When continental ice sheets take hold, they are not thin mantles, but beasts of mass and gravity. The Laurentide ice complex that once covered much of North America reached thicknesses measured in kilometers in its central domes. The ice was as tall as the highest mountains standing today. A similar crown sat over northern Europe and the British Isles, the Fennoscandian ice sheet growing into a domed glacier that flowed outward like a frozen tide. These were not inert blankets. They moved, creaking and sighing, sliding over bedrock, lubricated in places by meltwater that pursued subglacial channels like secret rivers. Ice is heavy, and under such enormous weight the crust flexed and bowed. Shorelines depressed, river gradients languished. The ground itself yielded to the load of white, and that yielding left marks that geologists can read, bulges and rebounds. Isostatic fingerprints that continue to shape coasts and seismology today. The landscape beneath those sheets was at once protected and erased. In some places the ice insulated and preserved, soils frozen beneath, organic matter trapped in permafrost, pockets of ancient ground undisturbed. In many more places the opposite occurred. Glaciers are voracious grinders. They turn mountains into flour, bedrock rasped into silts and sands known as glacial flour, transported downstream to become the lowest plains of distant continents or to fertilize productivity where meltwater met sea. The grinding action carved distinctive geomorphology. U-shaped valleys replace V-shaped river-cut canyons. Fjords form where glaciers chewed deep into coastal shelves and were later flooded by the sea. And jagged cirques and hanging valleys mark the places where tributary glaciers once joined greater ice arteries. The fingerprints of these processes are visible in the familiar geography of the present. The Great Lakes of North America are not lakes by accident, but bowls scooped by ice. Long Island, Cape Cod, and the morainal ridges of southeastern England are terminal moraines, the telltales of ices farthest breathing out. The smooth drumlins of southern Ontario and Ireland trace subglacial flow directions like a foreign hand's faint smears, and where the ice met the ocean, icebergs carved and drifted, depositing erratics, boulders born under one sky and dropped under another, creating a scattered gallery of geological strangers across plains that would otherwise have been homogeneous. Because ice moves slowly over long durations, the changes it enacts are both enormous in scale and layered in time. A continental ice sheet does not merely remove and distribute material, it also cuts, seals, and reshuffles the very template of drainage. Rivers are rerouted, catchments reorganized, and floodplains buried. In many cases, channels that for millennia carried the flow of fresh water were blocked by moraines and ice dams, producing vast proglacial lakes. When those dams failed, and catastrophic failures did occur, the results were violent and abrupt. The Missoula floods in the northwestern United States, unleashed when an ice-dammed lake repeatedly broke, scoured valleys into the channeled scablands, carved coulees hundreds of meters deep, and left behind an otherworldly topography of scoured basalt and erratic deposits. Such mega-floods were sudden punctuation marks on a slow-moving story, reminders that ice-age landscapes could produce episodes of terrifying speed and scale. Sea level, too, was a map-maker and map-changer. At the height of the last great glaciation, global sea level dropped by roughly 120 meters, exposing continental shelves as wide plains. These shelves were not barren. They were ecological zones, migration corridors, and human habitation zones that are today drowned and silent. Beringia, the land bridge that connected Siberia and Alaska, was a corridor of life during many glacial intervals, enabling exchanges of flora, fauna, and the earliest peoples between continents. The drying of shallow seas, the exposure of submarine terraces, and the creation of vast new coastal ecologies were as transformative to the living world as ice on the continents. When the ice retreated and sea level rose, entire chapters of habitation were submerged and sealed beneath sediments and salt, making the archaeological record inherently partial and biased. If European and North American ice sheets are the most dramatic examples, they are not unique. Glaciation reconfigured landscapes across high latitudes and high elevations worldwide. In the southern hemisphere, Patagonia bore great ice slopes that carved fjords and installed moraine amphitheaters in what are now temperate forests. Mountain ranges the world over hosted alpine glaciers that hollowed cirques and left hanging valleys. The depth of cold penetrated into permafrost zones, creating patterned ground and ice wedge polygons seen today in tundra. Pingos rose as groundwater froze and heaved the surface into domes. These periglacial features shaped drainage, influenced vegetation patterns, and hosted distinct ecosystems adapted to the rhythm of freeze and thaw. Not all transformations were straightforward erosive narratives. Some were paradoxically preservational. Permafrost, when persistent, can entomb biological material with uncanny fidelity. Mammoth carcasses found with flesh and fur intact, stomach contents visible, are tragic and eloquent testimonies to the preserving power of cold. Pollen trapped in lake sediments, records shifting tree lines and vegetational changes in exquisite microscopical detail. Yet preservation is patchy. The same regions that conserve some histories obliterate others. The grinding of ice is a selective amnesia. Soil horizons and fragile archaeological structures are vulnerable. Their absence is not proof of their non-existence. Among the most evocative counterpoints to the image of an ice-draped world is the idea that some places we now call deserts were once green. The Sahara, today a symbol of arid vastness, has not been a desert for all of the recent geological past. Orbital variations that shifted monsoon intensity drew the intertropical convergence zone northward during specific intervals, bathing North Africa in summer rains. The African humid period, which peaked around 10,000 years ago but fluctuated in earlier millennia as well, turned much of the Sahara into grassland and savanna punctuated by lakes, rivers, and reed beds. Evidence for this wetter past is written in Paleo-lake shorelines, now fossilized in pluvial sediments in the bones of hippopotami and crocodiles excavated from deposits hundreds of kilometers from the present Mediterranean, in the ochred petroglyphs and paintings left by human hands along newly vegetated shores. River systems, now buried and cryptic, once braided across basins and paleo-channels, suggest that lush corridors connected sub-Saharan Africa to the Mediterranean edge. These greener Sahara episodes are not mere curiosities. They reframe migration narratives and ecological possibilities. When deserts greened, they allowed humans and other species to traverse zones that later became impassable. Lakes served as hubs of biodiversity and as attractors for fauna, creating local hotspots of life and culture. Conversely, when aridity returned, those same regions became traps. Populations concentrated around shrinking water. Landscapes turned brittle and mobility became constrained. The rhythms of wet and dry therefore shaped not only the distribution of species, but also the trajectories of human movement and settlement. Taken together, the image of glaciated continents and green deserts reveals a pattern. The Earth's face was not uniform in its response to cold. While vast white dominions claimed northern expanses, subtropical regions could become paradoxically wetter or drier depending on the dance of monsoons and ocean patterns. The global climate was a mosaic, stitched from the local impacts of orbital geometry, ocean circulation shifts, and atmospheric teleconnections. Dust from desiccated regions, fine grains of pulverized glacial rock and desert sand, was lofted by fierce winds and redistributed across the planet. Lowest deposits in China and the American Midwest, formed of wind-blown silt, are the distant fingerprints of northern ice grinding in southern aridity. Those dust layers fertilized oceans and land, influencing phytoplankton, blooms, and soil formation in places far from their source. Ice also altered the chemistry of the sea and the air. The trapping of water in ice sheets changed ocean salinity and circulation patterns. Freshwater pulses from melting ice dams could inject into ocean basins and stall the conveyor belts of heat, with regional consequences for climate. Aerosols and dust loaded in the atmosphere altered radiative properties volcanic eruptions under cold climates had. Disproportionate climatic impacts. The carbon cycle itself responded. During glacials, atmospheric CO2 fell. During interglacials, it rose. Ice core records show these swings, embodying a feedback loop between biosphere, ocean, and atmosphere. Life was not a passive witness to these changes. It responded, changed, and in aggregate influenced the climate's trajectory. The mammoth steppe, a vast, cool grassland stretching across northern Eurasia and Beringia in glacial times, supported a suite of megafauna that in turn influenced vegetation patterns and nutrient cycling. The disappearance of such ecosystems at the close of the last glaciation produced cascading ecological effects. The human dimension of these transformations is both practical and existential. For the ancestors of modern humans, Ice Age landscapes were opportunity and peril in equal measure. Exposed shells and land bridges enabled migration, retreating ice opened new habitats. But the unpredictability of rapid climate swings, abrupt warming events, megafloods, and the sudden isolation of coastline resources forced adaptability. Societies adapted not only by moving, but by innovating. New tools for hunting in open tundra, storage strategies for seasonal scarcity, and cultural practices built around mobility. The record of human artifacts, however, is incomplete and biased by the processes of deposition and erosion. Many early coastal settlements were swallowed by rising seas, their traces now lying in dark underwater canyons. From the standpoint of preservation and loss, glaciation is a double-edged ledger. Its power to erase physical structures is matched by its tendency to produce new archives, deep lake sediments, varved clays, and ice cores that record atmospheric chemistry by the season. The planet remembers the Ice Age in many voices, in the polished bedrock of its highlands, in the fossil pollen of lakes, in the isotopic swings recorded in shells and ice bubbles, in the distribution of boulders perched where they could never have been born. Those archives are partial and distributed, and they privilege certain kinds of information over others. Hard chemistry and durable minerals persist, while ephemeral organic stories are the most likely to slip away. There is an effective logic to all of this that resonates with the themes of the deeper narrative. The scenes of kilometer-thick ice pressing on continents are at once humbling and terrifying. They remind that the arrangements now taken for granted, coastlines, rivers, fertile plains, are provisional. They also remind that change can be both slow and abrupt, that landscapes can be composed over millennia and then in a few wild years be reconfigured by the sudden failure of an ice dam. The duality of ice, its slow patience and sudden violence, frames an emotional landscape where human presence is necessarily limited and inventive. Finally, these glacial landscapes are not only ancient memory, they are active agents in the present. Isostatic rebound continues to alter coasts left bare by ancient ice. Permafrost thaw releases ancient carbon and reorganizes hydrology. Glacial meltwater shapes seas and sediments in ways that affect modern fisheries and storm dynamics. The past and present are braided, the marks of ice tell stories that are still being read. To listen is to accept the smallness of individual time and an amplified responsibility. The planet's climate operates on tempos that dwarf daily politics, but human choices are now part of those tempos. Understanding how ice sculpted continents, greening deserts, and exposing abyssal plains is therefore not an antiquarian pursuit, but a necessary rehearsal in planetary literacy, a way to recognize how landscapes can be lost, saved, or transformed, and how the traces of life, no matter how tenacious, are subject to larger, remorseless forces. In the end, the image remains: continents wearing white crowns, deserts that bloomed into lakes, oceans pulled back to reveal their former heights. Those images are not romantic relics. They are functional descriptions of a planet that has repeatedly remade its face. For anyone wishing to read the deeper history of Earth, its losses and preservations, its sudden collapses and patient recoveries, the glacial landscapes are both a library and a mirror. They show how powerfully and precisely the planet can erase and what kinds of evidence survive the eraser's stroke. They compel a stance of humility and attention. The present warmth is temporary, the map is mutable, the record is partial. And somewhere in that partiality lie both the keys to understanding past lives and the sobering prospect that much can vanish if the long processes of Earth are once again set to restless change. What does life become when cold is not an occasional adversary, but the organizing principle of a world? That image, not of a single frozen moment, but of an entire biosphere reconfigured to make the best of ice and scarcity, is the anchor of the 6th chapter. It is a question about form and function, about how anatomy, behavior, and ecosystems rewrite their rules when the climate insists on a different grammar. The inquiry is not merely zoological, it is philosophical. In those long winters, life did not only survive, it invented new ways of being warm, mobile, persistent, and surprisingly inventive. At the most visible scale are the megafauna whose silhouettes define the age: the woolly mammoths, the shaggy rhinoceroses, the saber-toothed cats. These are not theatrical actors in a story, but evolutionary answers to ecological problems. The woolly mammoth, proboscidean lineages adapted to open cold steppes, is a study in redundancy and amplification of protective traits. Thick, layered coats produced insulation not by a single strategy, but by combination: a long, coarse outer hair that shed wind and a dense underfur that trapped still air, substantial subcutaneous fat that buffered both. Thermoregulation and energetic swings across seasons, and a body plan with relatively short extremities that minimized heat loss. The tusks, curved and monumental, served multiple plausible functions beyond display. They could be used to sweep snow aside to reach buried forage, to break crusted ice, to lever soil and plant matter from frozen ground, and to resolve intraspecific tensions without exposing vulnerable facial tissues. The trunk, nervy and dexterous, became a multi-purpose tool for manipulation in a world where hands were not available. Evidence of these adaptations is not speculative flourish, but encoded in bones, preserved hair, and the molecular traces recovered from permafrost. Isotopic signatures in collagen narrate seasonal diets. Dental microware whispers of abrasive grasses and gritty winter fodder. Ancient DNA demonstrates not merely lineage, but genetic recombinations that increased cold tolerance. In other words, the mammoth was a whole system adaptation: morphology, metabolism, and behavior tuned to a biome dominated by cold and by the steppe's brittle productivity. The woolly rhinoceros was a parallel answer to the same set of constraints. Its broad, downward-pointing horn and robust neck musculature suggest a life spent in a world where snow was often the first obstacle between herbivore and food. The horn could sweep hard-packed snow and ice or excavate nutrient-rich plants beneath a white mantle. Thick skin and a dense coat reduced evaporative losses, and limb proportions favored steady travel across uneven, frozen substrates rather than speed over a soft plain. The rhinoceros is, in this register, a specialist for persistence, not the fastest, but the obstinate survivor. Predators, too, found their niches remade by the cold. The saber-toothed cats, iconic for their elongated canines and muscled forequarters, illustrate a predatory economy adapted for power over speed. These cats likely hunted large-bodied prey that inhabited open steppe, using ambush, social coordination, and overwhelming close-range force. The long canines delivered deep, perishable wounds to soft tissues. Robust forelimbs pinned prey long enough for a kill to be accomplished without the risk of long chases across exposed terrain. In the cold, where endurance could be compromised, and where vegetation offered sparse concealment, such a predatory morphology made ecological sense. These are striking images, but the real wonder lies in the ecological tapestry that supported them: the mammoth steppe. This biome, which stretched from Western Europe across Siberia into Beringia and down into parts of North America, was neither tundra nor the dense boreal forest that replaced it in many places after warming. Instead, it was a vast grass and forb-dominated landscape with low shrubs, lichens, and scattered sedges, an ecosystem of high productivity in cold, dry climates. The step succeeded in turning mineral-rich but frozen soils into biomass through unique seasonal phenologies, rapid summer growth, roots and perennials tuned to short growing seasons, and community structures resistant to frost heave and grazing. Mega-herbivores were ecosystem engineers on this plain. By trampling and grazing, mammoths and other large grazers controlled vegetation structure, prevented woody plant encroachment, and maintained open grassland habitats. Their dung redistributed nutrients across landscapes and sustained decomposer networks that were otherwise limited by cold conditions. Such engineering had feedbacks into climate and permafrost dynamics. Maintained open grassland may have reflected more sunlight than dark shrubs. Conversely, the loss of megafauna could permit shrubs and trees to advance, changing surface albedo and insulating the ground in ways that promoted permafrost thaw. It is a reminder that animal populations do not merely adapt to landscapes, they shape them. Smaller actors were no less inventive. The cryobiome, the community of organisms adapted to life in freezing and near-freezing conditions, composed a suite of biochemical and behavioral tricks. Microbial life in snow and ice cultivates pigments that reduce solar reflection and raise local temperatures. Cryophilic algae produce blooms of red and green that color snow surfaces and patches. Antarctic analogues show that even finely stratified glaciers can host microbial mats, pockets of photosynthesis under thin ice, and chemolithotrophic communities near geothermal upwellings. In the ancient cold, similar microhabitats could have persisted, reservoirs of primary productivity in an otherwise austere world. Physiological strategies spanned the macroscopic to the microscopic. Antifreeze proteins in the blood and body fluids of some cold-adapted animals prevent ice crystal growth and allow tissues to withstand sub-zero temperatures. Metabolic flexibility, shifts into torpor, hibernation, seasonal fat deposition permitted organisms to ride out periods of scarcity. Invertebrates and plants evolved desiccation tolerance and dormancy, preserving genetic lineages through long winters and seeds, spores, wine, or compacted cysts. These solutions were convergence and action, unrelated lineages arriving at similar biochemical and morphological outcomes because the environment imposed comparable constraints. The edge habitats, the boundaries between sea ice and open water, were particularly rich in paradox. Sea ice is structurally simple, yet ecologically complex. Algae and bacteria live within and beneath the ice, creating a thin but productive layer that seeds the food web. In polar analogues, seals and marine mammals exploit openings and leads, while birds time migrations to exploit seasonal pulses of productivity. In deep past glacial phases, polynyas, persistent open water areas created by winds or currents, may have acted as refuges for marine life and as oases for higher trophic levels. Such refuges could be disproportionately important, serving as evolutionary hotbeds where genetic diversity was conserved and from which recolonization could occur during warmer intervals. Even beneath permanently frozen sheets, life found purchase. Subglacial lakes, heated by geothermal gradients and isolated from the atmosphere for millennia, provide contemporary models for life beyond light. There, chemosynthetic processes, microbial communities powered by geochemistry rather than photosynthesis, can maintain biomass. In ancient, long-lived glaciations, similar sub-ice ecosystems may have been persistent refugia, insulated by kilometers of ice yet kept alive by the slow chemistry of rock and water. These systems complicate any simple narrative of ice as pure obliteration. The behavioral repertoire of animals under cold stress was also a key survival tool. Migratory corridors, such as those that crossed Beringia at times of low sea level, allowed genetic exchange and seasonal tracking of resources. Herding and social structures buffered individuals against predation and improved foraging efficiency. Storage behaviors, from caching plant matter to communal larders, ameliorated the sting of lean months. Fire, where accessible, remained a tool for creating habitat mosaics and for altering surfaces in ways beneficial to certain plant communities. These are cultural and natural behaviors alike, not narratives of heroism, but of repeated, practical adaptation. The archaeological and paleontological record provides many of these inferences. Coprolites, fossilized dung, pollen and phytolith records, stable isotopes in bone collagen, and ancient DNA fragments recovered from permafrost together produce a multi-scalar portrait of life in the freeze. Where megafaunal bones cluster, paleobotanical context permits reconstruction of diets and seasonality. Where permafrost preserves fur and soft tissue, molecular analysis reveals the biochemical strategies animals use to stay warm. The picture that emerges is of a biosphere improvising with available chemistry and morphology to keep metabolic fires burning. This is, however, not an eternal equilibrium. The systems of cold were poised on edges, thresholds of vegetation type, permafrost stability, and megafaunal population dynamics. The extinction of keystone species, whether by climate stress, human predation, disease, or a confluence of factors, could induce rapid ecological turnover. In some regions, the disappearance of mammoths and other megaherbivores coincided with the expansion of woody plants, soil retention and permafrost insulation in ways that changed carbon fluxes and landscape albedo. Such transitions are not mere extinction stories, they are cascades of biogeochemical reconfiguration, which brings the narrative to its seventh fragmentary heading, 7. Co. The terse label reads like a prefix awaiting completion, co. As companion, cooperation, codependence, co. As collapse, convergence, consequence. The intent can be read as an invitation to consider the intertwined fate of organisms and the systems they inhabit. Coevolution is the first theme. In cold worlds, species evolved in concert, predator and prey. Grazers and the grasses they kept short through grazing pressure. Microbes and plant roots engaged in nutrient cycling attuned to freeze-thaw rhythms. These co-adaptations generated networks of mutual reinforcement. The presence of a mega-herbivore was not isolated from soil microbes. The grazing that opened plant communities also redistributed nutrients that fed microbial activity, which in turn influenced plant regrowth. In this sense, the ecology of cold is deeply codependent. Co-extinction is the darker flip side. When a keystone species disappears, dependence can follow in rapid succession. Specialists that require the unique conditions maintained by ecosystem engineers vanish with them. The fossil record and genetic histories hold traces of these dominoes, sharp losses of associated species in the wake of megafaunal collapse, altered pollen records showing vegetation shifts, and changes in the size and range of predators forced to track scarcer prey. The co-extinction concept widens the moral imagination beyond single species to networks. Systems die not in isolation, but in concert. There is also the notion of co-responsibility between Earth systems and any intelligent agents that arise within them. If a pre-existing technological activity had ever overlapped with these cold ecosystems, their signatures would be modulated by ecological processes. Mining, metallurgical smelting, and landscape modification would leave chemical signatures that co-mingled with natural fluxes of dust, volcanic aerosols, and organic decay. These blended signatures will be harder to read precisely because the cryosphere is both an obliterator and a chemical conservator. Physical forms vanish, but isotopic and molecular whispers can persist. In short, the planet records the co-presence of nature and possible culture in layers that require careful disentangling. Finally, co-adaptation extends to timescales, climate systems, life, and continents co-evolve. The advance and retreat of ice alters the course of evolutionary pathways. Life's responses, in turn, feed back into atmospheric chemistry and surface processes. A biome that encourages hard, low vegetation promotes different albedo dynamics than one with tall forests. Animal community composition determines the fate of soils and carbon reservoirs. These are slow, co-authored pathways where no single agent holds authorship. The mood of these chapters is not merely scientific cataloging. It is an ethical and aesthetic meditation on scale and fragility. Observers looking back from the warm now may feel a double vertigo, admiration for the inventiveness of life, and an unsettling sense of how easily the scaffolding of ecosystems can be reconfigured by forces both slow and sudden. The evidence gathered from bones and ice, from DNA and sediment, argues that life in the freeze was neither a frozen tableau nor a fragile remnant. It was a living, dynamic system that innovated around constraints. Yet, it was also a system where losses could propagate, where the removal of a single thread could reorder an entire tapestry. The archive of the cold, the bones, the frozen hair, the isotopes and shells, the mats of ancient microbes, is precious precisely because it is partial. Ice grinds and buries, preserves and erases unevenly. The stories that remain are the result of energetic contingency, where permafrost sheltered organic material, where sediments rapidly sealed away chemical signatures, where post-glacial exposures revealed hidden layers. The fragments stitched together yield a portrait of life that is both robust and precarious, and that compels the modern observer to consider how present actions might be read in the future strata. In the end, the sixth and seventh meditations converge on a simple, unsettling conclusion. Life is astonishingly adaptive, but adaptation occurs within bounds. The cold epochs were times of great invention, physiological, behavioral, and ecological, and they produced landscapes and animal communities unlike anything in the modern temperate imagination. Yet those same epics reveal how networks of interdependence can be rearranged, sometimes irreversibly, by climate and by the actions of the species within them. The lesson the narrative leaves with the reader is an invitation to humility and to vigilance, to recognize the creativity of life in the face of planetary extremes, and to accept that the fragility of ecological networks makes stewardship an enterprise that must think not just in seasons but in the long, co-authored tempos of Earth itself. What does survival look like when the world's climate is not an inconvenience but the defining fact of existence? That question frames the study of humans in the Ice Ages, not as isolated anecdotes about a few individuals, but as a repeated, long-running drama in which species, technologies, and social forms were continuously tested by cold, scarcity, and sudden upheaval. In that theater, two hominin lineages, Neanderthals and Homo sapiens, occupied overlapping parts of the stage. They were different in anatomy and behavior, but they shared a set of fundamental problems: how to keep warm, how to make food reliable, how to move across a planet that reshaped itself under ice. The archaeological record gives the outline of their solutions. The residue of stone, bone, ash, and pigment supplies the clues. Stone tools are the most enduring of those clues, and they functioned less like inert artifacts and more like extensions of a living body. Flint, chert, and other nappable materials were selected, struck and retouched in techniques that reveal a thoughtfulness about fracture mechanics and ergonomics. The patterning of flakes along a core, the Levallois reduction strategy, the finesse of prepared cores, the later emergence of blades is not merely technical minutiae. It is evidence of planning depth, the ability to imagine a sequence of strikes that would produce a useful edge, and the capacity to teach that sequence to others. In an ice-clad landscape, where each harvest and each shelter mattered for survival, such skills were not mere craft, they were cultural lifelines. Fire is the other obvious instrument, but it must be considered as technology, social glue, and ecological tool all at once. Control of fire transformed the cold landscape. Hearths, concentrated heat, concentrated food processing, and concentrated social life. Around embers, calories were converted into bioavailable nutrients. Hides and sinews were dried and worked. Night, which in polar winters could be mercilessly long, became a time for repair and conversation. Fire altered predator-prey relations. It kept dangerous animals at a manageable distance and allowed humans to exploit resources. Bone marrow, tough plant tissues that would otherwise be inedible. Hearths also laid down stratified chemical records. Charcoal, ash, heat altered bone and stone, microstratigraphic markers that preserve seasonality and behavior in ways that are remarkably durable, even as larger structures are erased. Caves and rock shelters served as both refuge and archive. They were chosen for reasons that are instantly practical: shelter from wind and precipitation, proximity to fresh water, ease of access to game trails, and for reasons that are social and symbolic: the acoustic qualities of deep recesses, the constant microclimate, and the availability of secure sleeping places transformed some caves into long-term occupation zones. Within their dark interiors, soot-blackened ceilings and stone hearths were placed with care. Sleeping areas were swept, middens accumulated, and particular alcoves sometimes received elaboration in the form of pigment, incised bone, or arranged stone. Caves preserve well because they buffer against rain, sun, and wind, and so they disproportionately hold the traces that archaeologists now read as intentional. The darkness that once afforded warmth and safety now contains the fossilized palimpsest of human presence, layers of hearth ash like rings of memory, fragments of worked bone and antler, the spatial clustering of refuse that betrays organization and repetition. Hunting strategies in cold biomes demanded coordination and ingenuity. In a landscape dominated by megafauna, success required more than individual prowess. It required social choreography that could. Martial bodies and minds, herd animals that roamed steppe and tundra, elephants of the mammoth lineage, immense bison, and other large-bodied mammals were not simply prey, but ecosystem engineers whose presence structured the very habitats humans depended on. Hunters used natural topography and ephemeral features to their advantage, driving animals across frozen rivers and into narrow defiles, herding them toward ambush positions, or isolating individuals during seasonal migrations. Stone-tipped spears, thrusting tools, and later composite implements using bone, wood, and sinew made such strategies possible. The risk and thrill of the hunt are visible in fracture patterns on weapons, in cut marks on bone, and in sites where high concentrations of animal remains cluster around hearths and work areas. These are not random kill sites. They are records of planning, of tool repair, of cooperative meat sharing that kept the social group fed through months of scarcity. The emotional texture of life under ice can be inferred from repeated patterns. Investment in juvenile care apparent from healed injuries and long juvenile growth periods. Burial practices that suggest an awareness of personhood beyond immediate utility. The accumulation of ornaments and pigments that imply a symbolic life beyond mere subsistence. Wet burials are found, sometimes in rock shelters, sometimes beneath hearths. The presence of grave goods, body positioning, or the careful placement of stones speaks to a relation to the dead that transcends instrumentalism. These are not characters in a novel, but human communities forming meaning in the face of mortality. The grief of loss and the tenderness of caregiving are not merely speculations. They are the most plausible inferences from evidence that repeatedly shows repair of injured limbs, long-term care for disabled individuals, and investments in young that are costly but ultimately socially productive. Coexistence between Neanderthals and Homo sapiens complicates the picture in interesting ways. The fossil and genetic archives show episodes of overlap, contact, and exchange. Genetic traces in the modern human genome testify to past interbreeding. Lithic industries and settlement patterns sometimes indicate shared adaptations or borrowing. The interaction was not a single story of replacement, but a tangled web of encounters. Territories partially overlapped, technologies moved, and ultimately some lineages persisted while others vanished. From a documentary perspective, that entanglement raises further questions. How did cognitive repertoires overlap? Which cultural practices were adopted from neighbors and which were retained as identity markers? Archaeological layers sometimes show transitional toolkits, sites where different technological traditions intersect, and such places read like forensic scenes of cultural negotiation. Material culture extended beyond stone and fire. Clothing, stitched from hides and insulated by furs, was critical for thermal regulation. Evidence of sewing, the production of needles, and the careful finishing of garments indicates an attention to detail and an investment in labor that altered survival probabilities. Shelter making ranged from the use of caves to constructed structures, frames of wood, hide tents, and, in some regions, the reuse of massive bones as structural elements. The labor investment required to erect durable shelters speaks of cooperative economies and seasonal planning. Food storage, caches of dried meat and bone grease, and the selection of certain plant and animal resources for their caloric density are all behaviors that make sense only in the context of group-level coordination and long-term thinking. Language, while not directly fossilizable, leaves indirect traces in the complexity of social coordination evident in tool production, hunting, and the division of labor, teaching napping sequences, coordinating a multi-person hunt, and maintaining social norms around sharing and intergroup relationships all suggest communicative systems of considerable sophistication. Around a shared hearth, information about seasons, animal behavior, hide-curing techniques, and landscape memory could be exchanged and refined. Those oral traditions, the stories told to anchor rootways and to keep social knowledge alive, are the very types of cultural material most likely to be lost without a durable repository. The intangible record, songs, jokes, names, rituals, is the great lacuna in the archaeological archive. This lack of direct preservation is the heart of the ultimate mystery that shadows human prehistory. The earth keeps some things with tenacity and discards others without mercy. Bones and stones endure under certain conditions. Organic matter tends to vanish unless frozen, waterlogged, or rapidly sealed by sediments. Glacial processes are ambivalent archivists. Ice can entomb and preserve delicate tissues in permafrost for tens of thousands of years. The same ice, as it grinds across a landscape or heaves and collapses, pulverizes other traces to geological nothing. Caves protect and concentrate. Valleys scoured by ice erase and redistribute. The record that remains is therefore biased toward materials and contexts that favor preservation. That bias shapes the questions researchers can plausibly answer and leaves other inquiries about the full range of cognitive life, the depth of symbolic systems, the subtler forms of social organization. Necessarily speculative, chemical signals offer a different kind of archive. Isotopic analysis of bones and teeth reveals diets and mobility patterns. Microscopic residues trapped in stone tools hint at plant and animal processing, Soot layers in cave ceilings record episodes of burning and can be linked to the rhythmic return to favored sites. Even when large structures vanish under glacial scouring or riverine reworking, the chemical echoes of repeated human behavior may linger in soil horizons and sedimentary sequences. These whispers are subtle but instructive. They suggest continuity and change in subsistence strategies, the timing of seasonal occupations, and the breadth of exploited resources. The persistence of such chemical marks provides a methodological lifeline. Where form fails, signature may survive. The interactions between humans and megafauna are another layer of complexity. Large herbivore-shaped landscapes through grazing and trampling, their presence influenced plant communities and soil dynamics, which in turn affected human diets and mobility. The eventual disappearance of many of these species at the end of the Pleistocene, a phenomenon with multiple and contested drivers, altered the ecological scaffolding within which human societies operated. In some regions, the loss of megafauna coincided with vegetational shifts that changed fire regimes, soil accumulation, and carbon sequestration processes. These cascading effects underscore how human survival strategies were embedded within broader ecological systems. To understand one is to understand the other. The documentation of seasonality is one of the subtler triumphs of modern archaeology. Nestled sequences of ring growth in tooth enamel, cementum increments, and growth lines in mollusk shells enable reconstructions of annual cycles. These fingerprints reveal time-depth behaviors, camp movement timed to migratory pulses, resource scheduling that sped caloric risk across seasons, and the storage practices that turned ephemeral abundance into reliability. Such planning is the essence of long-term survivability in cold environments. It demonstrates a cognitive reach extending beyond the immediate, an orientation toward the next winter that required memory, prediction, and social transmission. Yet all of this careful engineering existed under the looming hazard of catastrophic events, sudden cold snaps, meltwater pulses that remade coastlines in generations, and the progressive advance of ice sheets that could swallow entire valleys. The record of abrupt climactic events, from stadials recorded in ice cores to mega floods carved by failed ice dams, provides a sobering backdrop. Human adaptations worked within a space of plausible futures, but nature's occasional caprices could, and did, deliver surprise. The cultural strategies that most reliably persist under such unpredictability are redundancy, mobility and knowledge, redundancy, multiple food sources, flexible social networks, and the diffusion of critical skills across groups. Finally, there is a moral and philosophical cast to reflecting on humans in ice ages. Reading the fragmentary archive fosters an appreciation for both the ingenuity and the fragility of social systems. It encourages humility. The survival of lineages and the longevity of cultural practices are not guaranteed insofar as they depend on delicate alignments of ecology, climate, and social cohesion. It also underscores an ethic of stewardship. The present climate and ecological trajectories are legible to any patient observer as processes that can reconfigure the conditions of life over surprisingly short spans. The long human past in cold worlds is thus not only a tale of endurance, but a cautionary mirror. The artifacts that have survived, the flaked stone, the charred hearth, the patterned deposits in a cave, invite contemporary listeners to consider what records our own era will leave, how durable they might be, and what mysteries will persist long after the daily dramas of our lives have become geological whispers. In the end, the story of humans and the ice ages is both concrete and enigmatic. It is concrete in the material traces, tools, hearts, bones, and pigments laid down in places that sheltered bodies and ideas. It is enigmatic in what those traces cannot fully convey, the warmth of an embrace, the cadence of a song, the precise shape of a myth. The archaeological voice is insistent and patient. It offers fragments and asks for careful inference. The deeper, enduring question, the ultimate mystery, at the edge of this chapter, is not whether humans survived the ice, for they clearly did in myriad ways, but what the full breadth of their inner lives looked like when survival demanded so much. That is the riddle that the cave walls, the hearth ashes, and the fractured stone leave for the listener, an invitation to imagine, with restraint and wonder, the forms of humanity coalescing around firelight in a cold world, shaping tools and stories that nevertheless might, in the sweep of deep time, be as ephemeral as footprints on a melting shore. What disappeared first, the giants or the remains of their world? That question sits at the hinge between paleontology and human imagination. Did the Earth's thaw erase habitats and with them the great beasts that once shaped landscapes, or did the presence of a small, Adaptable predator, newly spread and hungry, tip an already precarious balance. The extinction of woolly mammoths, saber-toothed cats, giant ground sloths, and a constellation of other Pleistocene megafauna is one of the late Ice Age's sharpest mysteries, a riddle whose answer reverberates through the narratives of human adaptation and the origins of civilization. The raw fact is stark. At the close of the last glacial maximum, across continents and islands, the faunal composition shifted dramatically. Species that had dominated steppe and tundra for tens of millennia dwindled and then vanished in geological heartbeats. In North America alone, dozens of genera, mastodons, mammoths, direwolves, and giant beavers among them, went extinct over a span of a few thousand years. Similar patterns, though regionally varied, appear in Australia and Eurasia. These were not mere local extinctions, they were broad, synchronous reorganizations of ecosystems. Three causal threads have been woven most often through the attempt to explain these losses: the slow hand of climatic change, the sudden and efficient pressure of human predation, and the specter of disease, pathogens riding on the new pathways of contact forged by mobile hunter-gatherers. Each thread is plausible on its own. Together they form a braided hypothesis in which the timing, geography, and ecology matter. The climate argument rests on a simple narrative. The world warmed. Ice retreated, sea levels rose, vegetation zones shifted northward or upslope, and the cold adapted steppe that had supported vast herds contracted. In many regions, forests expanded into former open plains. Permafrost thawed, hydrology changed, for creatures evolved to exploit the mammoth steppe, a unique biome with its own plant communities and seasonal cycles. These changes could have been devastating. The fossil record supports a rapid ecosystem turnover at the end of the Pleistocene. Pollen records show arboreal expansion. Isotopic analyses indicate altered plant diets, and sediment cores reveal changes in fire, regimes, and carbon cycling. In places where warming was abrupt, populations of specialists may have been given no time to adapt. Yet the climate story alone leaves uncomfortable gaps. Extinctions are often regionally asynchronous. In some areas, megafauna disappeared before a major warming pulse. In others, large animals lingered through considerable climatic oscillation. The spatial correspondence between the spread of humans and the chronology of extinctions argues for an interacting role. Here the overkill or blitzkrieg hypothesis enters: efficient human hunters, newly arriving into megafaunal realms, whether moving into the Americas across Beringia or down islands from continental sources, could have driven high-pressure hunting that a once plentiful but slow-reproducing megafauna could not withstand. The overkill model is compelling when set against basic population dynamics. Large-bodied mammals tend to have low reproductive rates. Their populations cannot sustain intense mortality. A combination of sustained predation on calves and young, disruption of migratory patterns, and localized overharvesting in critical habitats could cascade into regional collapse. Archaeological sites that preserve kill butchery marks on megafaunal bones, hunting blinds, and mass kill sites supply real evidence for human predation. Yet such direct evidence is not ubiquitous at the scale needed to explain all extinctions, and where it exists, it often appears patchy. That patchiness can be a matter of preservation bias. Coastal and riverine contexts are more likely to retain traces, while open steppe, repeatedly reworked by ice and wind, erases them. Thus, the silence in the archaeological record is not proof of absence. Between climate and hunting is the provocative possibility of disease. Pathogens, moving through ecologies newly connected by the mobile networks of humans and possibly commensal animals, could in theory precipitate rapid population declines. The arrival of a novel pathogen to a naive megafaunal population might have effects similar to the arrival of smallpox in humans. Populations on timescales far shorter than climatic trajectories. The disease hypothesis is difficult to evaluate in deep time because pathogens rarely leave direct signatures in sediments and bones. Unlike catastrophic fractures in stone or isotopic excursions, microbial epidemics dissolve into absence. Still, modern paleogenomics has begun to tease traces of ancient pathogens from permafrost-preserved tissues and dental calculus, blurring the line between improbable and plausible. An outbreak that disproportionately hit reproductive females, or one that was compounded by nutritional stress from dwindling forage, could have amplified the extinction signal already pushed by climate or hunting. The more likely reality is not an either-or, but an intersection. Climate change may have reduced population resilience, shrinking ranges and isolating groups into refugia. These confined populations, now genetically and demographically vulnerable, would be more susceptible to even moderate increases in mortality, whether from human predation, disease, or combined stresses like habitat fragmentation and wildfire. Humans, as flexible ecological actors, may have intensified pressure on key resources and altered habitat structure in ways that amplified natural stresses, intentional or incidental burning to maintain grasslands, overharvesting of keystone species, or the introduction of commensal animals and plants. In this coupled system, a small push can produce a large collapse, and the collapse of megafauna was not merely ecological, it was cultural. People whose economies, mythologies, and seasonal cycles were intertwined with the great mammals had to reconfigure their world. The disappearance of key prey items would increase the energetic cost of subsistence and could trigger demographic shifts, reduced population densities, greater mobility, or the compression of people into resource-rich refuges. In some regions, human groups diversified their diets, a phenomenon anthropologists call the broad spectrum revolution, expanding their use of small game, fish, shellfish, plants, and tubers. That diversification, it has been argued, is one of the preconditions for a suite of social and technological changes: storage, sedentism, plant management, and ultimately agriculture. This transition from Pleistocene mobility to Holocene settlement is a central thread in the story of civilization. The end of the Ice Age rearranged not only the plants and animals of the world, but the very substrates upon which social complexity could take root. As climate stabilized and summers lengthened, river valleys and coastal plains became reliable mosaics of resources. In those places, perennial plants could be tended, seeds stored, and seasonal surpluses accumulated. The rise of agriculture was neither inevitable nor instantaneous. It appears in different places at different times and under different circumstances: in the Fertile Crescent, in the Yangtze and Yellow River basins, in Mesoamerica, and elsewhere. But the common element is the newly favorable balance between predictable resource availability and human capacities for manipulation. Sea level rise, the great rewiring of shorelines as water returned from continental ice, is a particular historical twist in this transition. The end. Pleistocene melt drowned vast expanses of continental shelf that had previously served as corridors, foraging zones, and settlement locations. Today, many archaeologists believe that early coastal communities formed on those now submerged terraces and shelves, exploiting rich marine resources. The flood of the Holocene erased those habitats and buried their cultural residues under meters of sediment and salt water. The consequence of the gap in the visible record, whole chapters of maritime adaptation hidden beneath waves. Underwater archaeology over the last decades has begun to glimpse into this drowned world, revealing structures, shell middens, and tool assemblages, but much remains inaccessible. The sea, which had once been a resource, became a veil. The melting itself had paradoxical effects on preservation. In some places, thaw liberated context that had been frozen in time. Permafrost, that cold vault, has yielded exquisite snapshots: mammoth carcasses complete with stomach contents, ancient DNA intact, and plant remains that allow reconstruction of seasonal diets. These discoveries are window-like in their clarity. In other places, however, thaw is an eraser. Organic artifacts degrade, peat bogs oxidize, and microbial activity digests materials that had been locked away. Sea incursions truncated coastal sequences and introduced sedimentation regimes that buried, smothered, or chemically altered earlier deposits. Thus, the end of the Ice Age created both the conditions for new preservation and the means of destruction, a duality that complicates the archaeologist's task. The human response to these changes is the core of the narrative of civilizational emergence. With stabilizing climates and predictable seasons, risk could be managed in different ways. Storage of surplus food enabled larger sedentary populations, increased population densities fostered division of labor and the specialization of craft. Economic surplus supported a non-food producing class and allowed the emergence of governance forms that coordinated irrigation, trade, and conflict. Rivers, the Nile, the Tigris and Euphrates, the Indus, became arteries along which surplus flowed and urban life coalesced. Yet these very successes depended on a precarious balance. Built environments and intensive agriculture were vulnerable to flood, drought, soil depletion, and disease. The lessons of the late glacial world echo here. Ecological change can be sudden. Human systems can be resilient but brittle, and technological sophistication does not guarantee permanence. There is also a philosophical weight to the story of the thaw. In a mere few thousand years, landscapes that had been shaped by ice for the better part of an epoch were recast into conditions conducive to densely woven social fabrics. That rapidity, geological quickness in human terms, is humbling. It suggests that the window for civilization is contingent on a narrow corridor of climatic stability. The Holocene offered such a corridor, but it was temporary in the geological arc. The contemporary observer recognizes in this the double-edged mirror. Civilizations flourish in stable climates, but human activities can alter atmospheric chemistry and potentially narrow or shift those corridors. The question that loops back to the speculative horizon of earlier chapters is pressing. If a technologically sophisticated society had existed before or during the late glacial episodes, would the thaw have recorded or erased it? Here, the mechanics of preservation and erasure matter. Structures built on coast would be vulnerable to drowning. Those on river floodplains might be buried and then eroded by subsequent flow. Those beneath ice would be ground into sedimentary anonymity. Yet chemical fingerprints, anomalous concentrations of metals, isotopic excursions linked to large-scale metallurgy, molecular residues from synthetic compounds, might persist in sedimentary matrices. Radioisotopic anomalies, unless masked by later geochemical processes, could be particularly diagnostic. The thaw itself could both hide and reveal. Melting permafrost can expose ancient artifacts, while rising seas can entomb others under anaerobic sediments that are surprisingly good at preserving organics. Modern climate change adds an ironic twist to this archival narrative. The same processes that ended the Pleistocene, rising temperatures, permafrost thaw, sea level transgression, now unseal ancient contexts for study, but they also accelerate the degradation of what they unearth. Salvage, archaeology, and paleogenomics race against microbial appetites and chemical decay. In a cruelly apt symmetry, the thaw that allowed human civilizations to flourish also contained the potential to confound the fossil record of any civilizations that might have preceded them. The human story after the ice, then, is a tale of reconfiguration and invention born of constraint. The disappearance of megafauna did not merely remove prey, it reshaped cognitive ecologies. People invested in diverse subsistence portfolios, in territories that could sustain larger populations, and in storage technologies that smooth seasonality. They developed social systems capable of coordinating large-scale endeavors, irrigation, monumental architecture, the management of trade networks that characterized civilizations. Yet these trajectories were neither preordained nor universal. They are historical responses to a set of environmental contingencies, choices constrained by climate, technology, and social organization. In the end, the thaw is both a geological event and a narrative pivot. It erased and revealed, it removed ecological scaffolding and created conditions for new architectures of living. It forced humans to adapt, and in their adaptations it set the stage for the rise of complex societies. The interplay of climatic warming, human action, and disease, whether singularly or in combination, explains much of the late Pleistocene turnover in life and culture, but it is the consequences of the thaw that matter for those who imagine the arc of civilization, the drowning of coasts, the filling of river valleys with new sediments, the opening of niches for domestication, the rearrangement of social life around stored surplus. Those consequences are not only material, they are cognitive. They invite different ways of thinking about time, property, kinship, and the future. As this segment closes, the listener is left with a layered impression. The end of the ice is not a simple handover from a frozen order to a temperate one. It is a complex, messy reorganization where extinction, innovation, and cultural transformation co-occur. It is also, in a sobering way, an argument for humility. Human achievements, even those that seem durable, are written atop a substrate of deep geological processes. The megafauna that disappeared were ecological engineers of a magnitude that shaped climate feedbacks and vegetation patterns. Their loss rerouted ecological history in ways that directly affected the human pathway towards civilization. The thaw, by remaking the world, remade the possibilities for human life, and in doing so, it created the conditions for both the fragility and the extraordinary resilience of cultures that would, in time, write their own records into the planet's strata. What if the last act of the ice was not only to erase, but to midwife? That paradox of destruction yielding a new template for life is the quiet, consequential image that follows the retreat of glaciers. When ice withdrew, it did not simply vacate a landscape, it reorganized the planet's physical and chemical surfaces, exposing substrates that, in their newly liberated state, possessed a peculiarly potent combination of mineral bounty, water, and gentle topography. Those emergent plains and valleys became, in many regions, the raw material out of which agriculture could be invented and sustained. The retreating cryosphere, in other words, was both an eraser of the immediate past and an architect of a different kind of future. The mechanics of the architecture are granular and striking. As glaciers moved, they ground bedrock into a spectrum of grain sizes, from glittering clasts to the finest silts. That pulverized rock, glacial till, and the dust that would form loess, is a concentrated cache of minerals, phosphorus, potassium, calcium, and a suite of micronutrients crucial to plant growth. When the ice melted, meltwater streams redistributed this material, sorting and depositing it into broad outwash plains, deltas, and terraces. Proglacial lakes trapped fine sediments, allowing for the slow accumulation of deep, fertile silts in their basins. In other cases, wind picked up the finest particles and spread them across continents as lowest blankets, creating soil so rich and deep that, millennia later, they would sustain some of the world's most productive farmland. Water, too, came as both quantity and pattern. Meltwater created rivers with new courses, carved floodplains, and fed shallow lakes that moderated local climates. The seasonal pulse of melt provided a predictable rhythm, a surge of water in spring and early summer, nourishing young growth and replenishing groundwater. But glaciers depressed the crust and then retreated. Compensatory rebound, isostatic uplift, slowly altered drainage and shoreline positions, sometimes generating long-lived wetlands and marshes on newly rising land. These hydrological legacies were not merely resource reservoirs, they were ecological engines. Floodplains spread nutrients across landscapes with each inundation, and wetlands trapped organic matter, building up peat layers that would become repositories of carbon and proxies of past vegetation. Equally significant was the reworking of topography. The bowls and troughs carved by glacial scouring became lakes, over-deepened valleys filled with water and, later, with sediments that formed fertile basins. Where glaciers left behind moraines, ridges of unsorted rock and soil, they created natural levees and terraces, eskers and kames. The sinuous ridges and hummocky mounds formed by subglacial streams lent themselves to pathways and elevated, well-drained locations for early settlement. The geomorphology of a post-glacial terrain therefore offered an array of options for human use. Elevated, dry knolls for dwellings, flat plains for cropping, river mouths for fishing and transport. Ecological succession followed with elegant predictability. Bare ground, warmed and dried, lichens colonized first, breaking rock surfaces and initiating chemical weathering. Mosses and grasses followed, stabilizing soils and trapping dust. Over decades and centuries, as organic matter accumulated and microbial communities took hold, the nascent soils developed structure and fertility. Trees then moved in where climate allowed, forming the first pioneer woodlands that would evolve into more complex forests. In other locales, where aridity or cold constrained tree expansion, grass-dominated steppes became stable, productive ecosystems suitable for grazing. This vegetational choreography set the stage for a new relationship between humans and the land, an opportunity to plan livelihoods around recurring seasonal patterns rather than the unpredictable scatter of glacial times. The transition from mobile lifeways to the experiments of sedentism and cultivation was neither inevitable nor immediate. It was, however, rendered more feasible by the combination of predictable water, nutrient-rich soils, and microclimates created by water bodies and sheltered valleys. Where reliable riverine flooding deposited fresh silt each year, communities learned the value of timing sowing to the melt pulse. Where lakes and wetlands offered fish and reeds alongside game, human groups could diversify diets and plan for the lean season. Storage, drying, smoking, storage in pits and later in pottery reduced seasonal risk and allowed for the beginning of surplus accumulation. The practices that defined early agriculture were, in their essence, technologies of time and risk management. Selective harvesting and intentional planting of seeds were simple cognitive leaps with profound consequences. A move from immediate returns to the deferred calculus of reproduction and storage. People began to favor certain plant phenotypes, larger seeds, non-shattering seed heads, setting in motion unconscious selective breeding that would, over generations, transform wild grasses into cereals. Animal management followed parallel trajectories. Some herds were encouraged to linger, their young protected, their movements corralled. The domestication of plants and animals did not appear as an overnight revolution. It emerged as a mosaic of local innovations. Across fertile, post-glacial landscapes, material innovations reinforced these behavioral shifts. Simple implements, Digging sticks, hoes, ground stone tools improved the capacity to cultivate stubborn soils, while pottery enabled better storage and cooking. Irrigation and rudimentary canal works appeared where people harnessed meltwater to regulate supply, boosting yields and enabling denser settlements. Terracing, adopted in steeper glaciated valleys, prevented erosion and expanded arable area. The architectural forms of storage, pits, bins, and later granaries, signaled deeper investments in place, and these durable structures would, in some cases, be the first persistent marks of human engineering visible in the geological record. Warming after glaciation was therefore more than a climatic convenience. It was a turning point in the structure of human society. Predictable seasons allowed for accumulating surplus, and surplus made social differentiation and specialization possible. As storage facilitated population growth, labor could be divided. Some members intensified food production, others engaged in pottery, weaving, or trade. Surpluses flowed along emergent trade routes, fostering exchange networks that knitted distant valleys and coasts together. The demographics of density created new social imperatives: coordination, leadership, conflict resolution, and slowly complex forms of social organization emerged. Cities, in this view, are late and aggregated consequences of millennia of small, incremental changes in how communities manage resources in landscapes inherited from ice. Yet the agricultural promise carried with it an archival paradox. The very processes that fashioned fertile land also became agents of erasure for earlier traces. Floodplains that built deep, productive soils would bury the remnants of transient hunter-gatherer camps. The grinding action of meltwater reworked sediments into packages that hid or destroyed organic artifacts. Meanwhile, human practices themselves, clearing, burning, plowing, began to alter pollen records and soil chemistry, imprinting a cultural signal within natural archives. The archaeologist of the future reads these palimpsests. Abrupt rises in charcoal indicate intensified burning regimes. Shifts in pollen spectra reveal the expansion of domesticated species. Stratified terrace fills and canal silts are the fingerprints of irrigation. In short, agriculture writes itself into the geological ledger, sometimes preserving its own history and sometimes eradicating the fragile traces of what came before. The imprint of glacial retreat on the emergence of agriculture is also legible in a distributional logic of early civilizations. River valleys and alluvial plains that originated, in many cases, from glacial and post-glacial processes became cradles of complex societies. The nutrient fluxes and water regularity of such valleys allowed for intensive cultivation, while the corridors formed by rivers facilitated exchange and diffusion. Where topographic constraints forced cooperation over irrigation, in terraces or shared canal systems, institutions capable of managing common resources arose. Thus, the retreat of ice indirectly shaped the social landscapes of the Holocene. The map of fertile land inherited from glaciation structured where dense populations, complex economies, and hierarchical governance first took root. 10. Yutish bisanga, kan, li, inga. The traces of ice that remain today, long after ice ceased to cover vast expanses. The planet kept the memory of that cover in a geometry of landforms, sediments, and chemical signatures. The evidence is both obvious and subtle, enduring in shapes that traverse scale from a single boulder to entire lake basins. The most immediate signatures are geomorphological. U-shaped valleys, with their broad floors and steep sides, are textbook relics of valley glaciers. Fjords, drowned glacial troughs, are coastal cathedrals of ice's former reach, their deep, cold waters often hosting unique marine ecologies. Moraines stand as ridges of unsorted debris marking the maximum extents of ice lobes. Drumlins, those smooth, teardrop-shaped hills, indicate the direction of ice flow. Eskers snake through plains as sedimentary records of subglacial river systems. Erratic boulders, often compositionally foreign to their current surroundings, are mute witnesses carried great distances on the soles of moving ice. In many regions, large lakes, the Great Lakes of North America, for instance, occupy basins carved and deepened by glacial scouring, their dimensions and orientations aligned with former ice dynamics. Sedimentary archives carry a different kind of memory. Varbed clays, annually laminated sediments deposited in glacial lakes, encode seasonal rhythms like pages of a calendar, allowing the reconstruction of annual to decadal patterns. Drop stones embedded in fine-grained marine or lacustrine muds betray the presence of ice-rafted debris, pieces of rock dropped from melting icebergs into otherwise calm sediments. Lowest deposits, accumulated from wind-blown glacial flour, form thick, fertile blankets whose stratigraphy delineates changes in aridity and wind regimes. Within these sediments, chemical proxies, isotopic ratios of oxygen and carbon, assemblages of pollen, and biomarkers of ancient plant communities narrate transitions in temperature, vegetation, and biogeochemistry. Periglacial and permafrost features are living legacies of cold. Patterned ground, sorted stone circles, and polygons are sculpted by freeze-thaw cycles in high latitude and high altitude zones. Pingos, ice-cored mounds, and thermokarst depressions arise where permafrost dynamics alter ground ice. In some regions, permafrost itself continues to act as a time capsule, preserving organic matter, plant remains, and even whole carcasses for tens of thousands of years. These frozen vaults have yielded invaluable windows into past ecologies, preserved DNA, pollen, and stomach contents that reconstruct diets and seasons. They also, however, present a new urgency. As climate warms, permafrost thaws, releasing ancient carbon and microbial life, accelerating decomposition and potentially amplifying present-day greenhouse forcing. The relics of ice thus interact directly with contemporary climate dynamics. Human landscapes bear glacial signatures, both obvious and hidden. Terrace walls following moraine lines, river courses set by meltwater passage, fertile lowest plains turned to wheat fields. These are mundane expressions of ice's legacy. Yet other traces are more subtle, raised beaches from glacio-isostatic adjustments marking former sea levels, drowned coastlines, full of archaeological silence where early maritime communities once lived on, now submerged shells. Urban centers, farmland, and transport routes frequently occupy landforms fashioned by ice. The consequence is an almost uncanny intimacy. Human civilizations built their foundations on the reconfigured surfaces produced by long-vanished glaciers, often without recognizing the depth of that inheritance. At the chemical level, the planet keeps fingerprints that reach far into time. Oxygen isotope records preserved in marine carbonates and in ice cores reconstruct past temperatures and sea level changes. Carbon isotope excursions and spikes in certain trace metals can indicate episodes of rapid environmental change or human-induced perturbation. Where agriculture intensified, anthropogenic signals accumulate, elevated phosphorus in soils, changes in nitrogen isotopes due to manuring, layers of charcoal from landscape burning. These molecular and elemental traces are robust in different preservation contexts, and they form the analytic backbone for discerning the interplay of natural and cultural processes across the Holocene. There is also a physiological and biogeographic memory. Species distributions still trace pathways left open by retreating ice. The ranges of certain tree taxa march along post-glacial routes. Genetic lineages of plants and animals reflect refuge-aware. Populations survived glacial maxima. The very composition of modern ecosystems, which species dominate, which communities prosper, is a palimpsest of Ice Age movement and post-glacial recolonization. Finally, the traces of ice are entangled with contemporary questions of hazard and resource. Glacially fed rivers remain crucial water sources for millions, but they are sensitive to changes in glacier mass and in seasonal melt timing. Glacial retreat in mountainous regions threatens to reduce late summer flows even as spring floods intensify, complicating agricultural planning. Proglacial lakes can dam and then fail catastrophically, producing glacial lake outburst floods that devastate downstream communities. And permafrost thaw threatens infrastructure built on once frozen ground while releasing greenhouse gases that feed back into planetary warming. The remnants of ice, then, are not inert museum pieces. They are active agents shaping the living present. In the end, the traces left by glaciers form a double-edged legacy. They created many of the conditions that made agriculture, and through agriculture, the possibility of complex civilization, feasible. They deposited the silts and sands that feed rivers and build soils. They carved basins that became lakes and corridors for migration. They modulated climate and water cycles in ways that could support density and surplus. At the same time, they scrambled earlier records, ground ephemeral artifacts into sediment, and left an archive that privileges certain forms of memory over others. Their echoes are written in stone and silt, in isotopes and DNA, in the very contours of fields and cities. For a civilization attentive to its own place in deep time, this is both a humbling and an instructive fact. The warmth that allowed for agriculture is transient on geological scales. The land that sustains food and memory was itself composed by agents indifferent to the needs or ambitions of any single species. To read the traces of ice is to read an instruction on contingency. The conditions that make human flourishing possible are products of processes vast in scale and indifferent in intention. The planet, in its glacial and post-glacial cycles, supplies both the stage and the props. Humanity's task, in the long view, is to learn how to live with that inheritance, to recognize the geological labor that fed its origins, to attend to the fragility of the systems that persist today, and to remember that what survives in the rock record is not the loudness of a moment, but the persistence of signals that outlast transient triumphs. What if the marks the earth carries today are not merely the memory of a cold past, but a ledger that writes into the present, a ledger whose entries invite a single unsettling question: could the planet turn white again? That provocative image sits at the edge of this chapter. It asks the listener to read contemporary places as living archives, the Great Lakes as scooped bowls of ice's appetite, the Alps hanging valleys and thinning tongues of blue-white melt, the broad North European plain as an inheritance of tills and loess that shaped the agrarian cultures of millennia. Those landscapes are not passive scenery, they are active testimony. They tell a story of what glaciers did, of what they left, and of what might, in principle, return. The Great Lakes are an anatomical lesson in glacial carving. They do not look like lakes that accumulated by chance. They are large basins sculpted by ice with a weight and motion of continental sheets gouged bedrock into deep hollows. Standing at a cliff above a lake today, the listener can almost read a slow-motion film, ice advancing, pressure increasing, meltwater lubricating basal zones, the grinding of bedrock into long, smooth troughs. The rims of those basins, moraines and drumlin fields, are not decorative but functional. They mark margins where ice paused, stored debris, and later receded. The feeling evoked is precise and melancholic. The Great Lakes are beautiful, used and loved, but they are also scars. They remind human imagination that hollowing can be made by patience as surely as by violence. The basins stored decades and millennia of sediment, each layer a page, fine silts that settled in post-glacial lakes, coarse tills that were dropped like broken teeth at the ice margin, pollen that whispers which plants first colonized newly freed ground. Those archives are public and accessible, and they teach the disciplined listener how to read the tempo of retreat and resurgence. The Alps speak in a different register. Altitude compresses time into a very physical language. The glacier-carved cirques and U-shaped valleys bear witness to alpine ice that ate through rock and left ridgelines serrated and sharp. In summer, the remaining glaciers are lacework, tongues of ancient ice that have, in recent decades, thinned and retreated with dramatic speed. The change is visceral. Blue ice that once filled a valley now sits as a shrinking shelf above bare stone, and every year more ice peels away. That retreat is a contemporary drama, recorded in photographs, in stakes drilled into ice and later exposed by melt. In the newly revealed moraines that were once hidden, the Alps are simultaneously archaeological site and active climate thermometer. They preserve in their geomorphology and in sample cores a record of past oscillations, advances when winters were sustained, retreats when summers sharpened. The emotional flavor here is tightly focused, a sense of urgency born of recent loss, coupled with awe at how much geological labor produced the present hollows where towns and valleys now sit. The North European plain is quieter but no less eloquent. Where ice lobes once pressed south from Scandinavia, the plain now supports a mosaic of soils and human settlement patterns that owe their character to glacial deposition. Thick layers of glacial till and overlying loess, wind-blown silt derived from glacial flour, created some of the most fertile agricultural lands in Eurasia. Cities, villages, and transport networks trace these fertile corridors. Hidden beneath fields are the sorted and unsorted sediments of ice's activity, kettles that became ponds, moraines that became elevated ridges where roads and settlements concentrate. The plain is also a library of erosional and depositional episodes, river terraces that mark stages of meltwater flow, peat bogs that accumulated in depressions and preserve pollen sequences, and buried soils that record the succession from tundra to steppe to forest and farmland. If a civilization wants a stable base for agriculture, it often finds it on land shaped by the last great ice. The irony is sharp. The ice that once threatened human existence left the very materials that allowed dense populations, technological specializations, and historical continuity to develop. These contemporary scars teach an important lesson. Glaciation is both erasure and gift. It destroys and creates, grinds and fertilizes. Where the ice once removed the fragile ephemera of a prior age, it also deposited foundations for a different kind of abundance. The Great Lakes, the Alps, and the North European plain are not relics frozen in amber, they are dynamic palimpsests. They invite a fundamental scientific as well as existential question. Given the natural rhythms of the planet, given the way insulation changes and feedbacks accumulate, could the rhythm swing again toward a new widespread glaciation? And, if so, what will be the shape and actors of that return? The scientific short answer is nuanced and, at times, counterintuitive. The machinery that has orchestrated the ice ages is well understood in broad outline. It is the slow arithmetic of celestial mechanics. The Milankovitch cycles, acting through subtle changes in orbital eccentricity, axial tilt, and precession. These cycles alter the distribution of incoming solar radiation, especially in northern high-latitude summers, and therefore set the stage for whether winter snowfall tends to persist year to year. In phases, when summer insolation at high northern latitudes is relatively low, winter snow is more likely to survive summer melt, accumulate, compact into ice, and begin the slow upward climb into a continental sheet. A past rhythm of glacial interglacial swings owes its beat to these orbital nudges amplified by feedbacks, ice albedo, greenhouse gas concentrations mediated by ocean chemistry and biology, and carbon sequestration by rock weathering and terrestrial ecosystems. But the present is not the pre-Anthropocene clockwork. The last few centuries, and especially the last century and a half, have placed a powerful new lever on Earth's thermostat. Greenhouse gases in the atmosphere, carbon dioxide, methane, and other anthropogenic agents have raised the radiative balance in a way that overlays and, for the foreseeable future, dominates the orbital signals that would otherwise steer the climate toward the next glacial inception. In simple terms, even if the orbital geometry in tens of thousands of years would favor growing ice, the elevated greenhouse gas concentrations today and for many centuries ahead act like a blanket that warms a planet and prevents the critical summer cooling needed for ice sheets to build. That is not speculation, it is the interpretation climate scientists have developed by coupling models of orbital forcing with carbon cycle dynamics and paleoclimate reconstructions. The implication is striking. Where, absent human influence, a new glaciation might be expected in on the order of tens of thousands of years, a time span that, to generational thinking, feels astronomically distant, yet geologically brief. The current atmospheric composition alters that schedule. In some model scenarios, anthropogenic greenhouse forcing delays or suppresses the next glacial inception for tens of thousands of years, perhaps much longer. The planet still follows orbital beats, but the amplitude and direction of the response have been fundamentally misaligned by human action. There are still caveats that demand attention. First, regional cooling episodes can and do occur against a background of global warming. Abrupt changes such as large freshwater inputs into the North Atlantic, meltwater pulses from collapsing ice domes, for example, can interrupt or slow the Atlantic meridional overturning circulation, producing marked regional cooling in the North Atlantic realm and associated climate anomalies in Europe. Those shifts can feel like a return to glacial conditions in some locales, even as the global mean temperature climbs. The new ice age, imagined in popular culture, a rapid, wholesale freeze enveloping continents in decades, is not a realistic projection based on present dynamics. Instead, any significant readvance of ice would require sustained changes in insulation and greenhouse forcing to align in a way that favors persistent accumulation. Second, the geological timetable has many levers beyond orbital forcing and greenhouse gases. Tectonic uplift, alterations in ocean gateways, the long-term weathering of new mountain ranges, and volcanic outgassing are all slow variables that modulate Earth's climate on long timescales. Human activity now adds a novel fast variable. The interaction of all these processes creates a space of uncertainty. Models provide a range of outcomes rather than a single prediction. Yet the dominant and robust conclusion is that anthropogenic perturbation is large enough to override the orbital nudges that otherwise would have favored glacial inception in the near-term geological future. The narrative consequence of this science is philosophically loaded. On one hand, humans have, perhaps unintentionally, removed an ancient risk, the return of continental-scale ice from the near-future horizon. On the other hand, that removal is not an unambiguous benefit. The extended period of warmth comes with its own suite of destabilizing outcomes: accelerated sea level rise, permafrost thaw and carbon release, shifts in precipitation patterns, and the loss of mountain ice that feeds rivers. Those consequences matter for the distribution of human populations, for ecosystems that evolved under seasonal rhythms, and for the very archaeological and geological archives that future readers might consult. In other words, the future absence of new ice as a global state does not equate to climate peace. It reconfigures the risks and the agents of change. There is also a deeper moral and temporal observation embedded in this science. The zero point of responsibility stretches far beyond political cycles and even beyond human lifespans. When greenhouse gases remain elevated for centuries to millennia, they become part of the boundary conditions of Earth system trajectories. Their legacy can suppress events that otherwise would have played out under orbital forcing, but can also set up new feedbacks that shape the planet's climate for epochs. The Anthropocene thus reads as a chapter where a single intelligent species alters the tempo and the palette of planetary states. An act that will be legible in sedimentary chemistry, in ice core ratios if ice cores persist, and in the very distribution of permafrost and glacial landforms. This altered ledger raises practical and ethical questions. If the next glaciation is delayed by human emissions, what should be the horizon of human planning? Infrastructure and agricultural systems are typically designed for decadal to centennial climates when the baseline itself is being shifted for millennia. What does stewardship mean? How does society account for slow planetary processes that will outlive any governance regime? Those are not technical questions alone, but existential ones. The present generation's emissions have effectively written a chapter into the climate ledger that future geologists will read as a distinct layer, a synchronous, globally spread signature of chemical change. The power to alter whether, when, and how ice returns is now a distributed human responsibility, whether or not it was intended. Finally, the listener must confront the contingency of memory. The present scars, Great Lakes, Alpine cirques, European loess, are legible now because they are recent enough and because human activity has left them accessible. A future ice advance would have different implications for preservation and erasure. It would scavenge valleys, bury shores, and remold sediments in ways that would seal and scramble the archaeological record that the Holocene civilizations have produced. Conversely, the current human imprint, greenhouse gases, synthetic compounds, linear features like roads and ditches, deep mining scars, will not vanish quickly. In the strata of centuries to millennia, these will be signals, and their detectability will depend on complex processes of burial and transformation. The question of whether another ice age will come is therefore not a question destined for a single empirical answer alone. It is a hinge between scales of time and frames of responsibility. The planet's cold episodes are neither caprice nor divine intervention. They are outcomes of physics and chemistry, of orbital rhythms and the slow machinery of geology. But for the first time in Earth's recent chapters, a technological species has gained the capacity to overprint those rhythms. That is the strange and sobering fact. The next major state change, an advance of ice or its continued absence, will be influenced by choices made in a narrow human window. The present fragile warmth that nurtured agriculture in cities is not a default to be taken for granted. It is both a gift of past geological labor and a fragile outcome held in part by human hands. To stand on the shore of a great lake, to watch the ragged retreat of an alpine glacier, to plow a field on tills laid down by an ice that no longer moves, these are experiences that teach humility. The planet's scars are eloquent, but their meaning is not fixed. They are read through the science of mechanics and chemistry, and they are colored by the ethical weight of action. Whether ice will return on a global scale is a question that science can bound and weight, but it is a question that humanity already has a hand in answering. The deeper takeaway is that the succession of states Earth cycles through, white and green, arid and wet, glaciated and temperate, is not an indifferent backdrop to human life. It is the theater in which civilization writes and erases its own possibilities. Listening to those scarred places now is an invitation to consider the long ledger and the signature that will be left on it. What if the present warmth is nothing more than a long, thin sigh of the planet, a pause between deeper breaths of ice? That question opens the final chapter, a thought that refracts through millennia of rock and ice and lands, and then returns to the one species that currently writes its mark in geology. The Earth still moves to the slow mathematics of its orbital dance, the long-wave rhythm of glaciations. Punctuated by feedbacks in oceans, rocks, and life, has not been suspended. Instead, what humanity faces is a paradox. The planet remains within a broader pattern that tends toward ice on sufficiently long timescales, yet human activity has become a force capable of bending, delaying, or displacing that natural cadence. In the modern laboratory of paleoclimate, prediction is both art and arithmetic. Scientists read the past as if it were a complex score, oxygen isotopes in foraminifera shells, the layers of ice cores with trapped bubbles of ancient air, the chemical fingerprints in cap carbonates, the scars of glacial till and loess. These archives provide the inputs for models, mechanistic reconstructions of atmosphere, ocean, ice sheets, and biosphere that allow a conditional forecast. Under natural boundary conditions, with greenhouse gases at pre-industrial concentrations and orbital forcing following its prescribed slow cycles, models converge on a familiar theme. At certain configurations of tilt, precession, and eccentricity, summer insolation in the high northern latitudes declines sufficiently that winter snow survives summer to accumulate. Given enough time and the coordinated responses of ice albedo feedbacks and carbon reservoirs, that accumulation can seed a new glacial inception. That is the simple skeleton of prediction. The flesh, however, is full of contingencies. The rate at which ice can grow is a function of seasonal temperature, but also of precipitation patterns, of whether continental shelves and mountain ranges provide nucleation platforms, and of the carbon content of the atmosphere and oceans. Ice sheets remember their own history. Hysteresis in the system makes them slow to start and slow to stop. A nascent ice mass that reaches a certain threshold becomes self-reinforcing. Greater elevation cools the surface. Higher albedo reflects more sunlight. Bedrock depression and drainage reorganization lock the system into persistence. To remove such a mass later requires a degree of forcing that exceeds the threshold that created it. Into this complex, patient calculus humanity has interposed a short, intense burst of greenhouse forcing. The combustion of ancient organic matter, the alteration of landscapes, the release of methane from wetlands and fossil fuels. These have raised atmospheric CO2 and methane to concentrations that had been rare in Earth's recent million-year history. These gases trap outgoing long-wave radiation. They are not ephemeral curiosities, but slow-acting agents whose residence times stretch across centuries and longer. By adding this supplemental heating, humanity has effectively placed a warm, insulating layer over the planet's thermostat. The consequence is twofold and deeply ironic. On geological timescales, the increase in greenhouse gases acts to delay, and in some modeled scenarios effectively suppress, the orbital conditions that would otherwise favor glaciation in the near-term geological future. A natural sequence that might have nudged the Earth back toward ice in tens of thousands of years can be postponed. A pause of many multiples of that interval by anthropogenic emissions. In that sense, human activity can be read as reversing a natural rule where the Earth's long-term tendency might be toward recurrent glaciation. The rapid injection of greenhouse gases throws the system into an alternative trajectory. But the same human agency that buys time against one kind of planetary risk creates new and immediate ones. Preventing glaciation does not equate to security. The warmth that humanity has engineered is neither evenly distributed nor benign. The cryosphere thins and recedes. Mountain glaciers that feed rivers are shrinking. Permafrost, a repository of carbon and ancient microbial life, is thawing, releasing greenhouse gases and altering hydrology and infrastructure. Sea level rises as polar ice and thermal expansion add water to the oceans, drowning coastal archives, reshaping economies, and redistributing habitats. Ocean acidification undermines shell-building organisms and reconfigures marine food webs. The very act that forestalls one slow catastrophe risks accelerating a suite of others, some of which will unfold quickly enough to be socially catastrophic: coastal displacement, agricultural disruption, and abrupt regional climate changes like shifts in monsoon patterns. Prediction in this context becomes less a forecast of a single outcome and more a mapping of probabilities across coupled systems. Models can show that, with sustained high greenhouse concentrations, the base state of the climate system will be warmer for millennia, enough to stand against orbital nudges whose cooling influence in the present chemical envelope is insufficient. Yet these models also show that the climate system is not strictly linear. Instantaneous and regional reversals remain possible. Freshwater inputs from rapid melt can perturb ocean circulation, like the Atlantic meridional overturning circulation, producing regional cooling even as the global mean temperature rises. The planet can be simultaneously warmed and unbalanced, a duality that confounds simple narratives of warmer equals safer. The ethical frame of this conclusion is unavoidable. The ability to delay glaciation is not mere technical trivia. It is a rewriting of the planetary ledger that will register under multiple proxies for deep time. The Anthropocene, already visible as a layer of microplastics, synthesized compounds, novel isotopic mixes, and a synchronous spike in greenhouse gases becomes a geologic chapter. Future readers of Earth's strata, long after current political orders and daily economies have dissolved, will find a thin, globally distributed signal, a chemical stratum that testifies to a species that fundamentally altered atmospheric chemistry. That is power of an unusual kind. Human action has become a component of boundary conditions for the planet's future states. Prediction and responsibility are thus necessarily married. If the models suggest that human emissions will postpone the next glacial inception by tens of thousands of years, then the question becomes not whether humanity can alter planetary trajectories, but whether it should. The calculus is not purely scientific, it is moral and temporal. To choose a path is to determine which hazards are deferred, which abated, and which newly emerged. The collective decision, whether explicit or the de facto result of continued emission trends, will be the signature future. Sediments read back. There is another, deeper layer to the predictive question, detectability and legacy. Throughout the earlier chapters, the narrative asked how the planet kept its memory and how eras of cold and warmth write themselves into geology. If human action prevents ice from returning on a timescale predicted by orbital mechanics, what will that mean for the preservation or destruction of the records humanity leaves? The same processes that rewrite climate also alter the ways in which biosignatures and technosignatures are archived. Rising seas drown coastal cities and bury them under anaerobic sediments that can preserve organic matter in surprising detail. Thawing permafrost can expose ancient remains that decompose if not promptly conserved. Erosion, sedimentation changes, and human land use will reshuffle the stratigraphic record. In short, the behavioral and chemical footprint that defines the Anthropocene will be filtered through geological processes whose tempo humanity now influences. This long view reframes familiar policy imperatives as matters of planetary legacy. Reducing greenhouse gas emissions is not merely a defense of contemporary interests, it is an act that preserves a broader range of possible futures. Lower emissions mean the planet remains closer to pre-industrial chemical states, leaving more of the Ice Age rhythm intact and making glacial inception possible again on its natural timetable. Higher emissions push the system farther into a warm state, one with its own novel hazards and a markedly different sedimentary signature. Neither option is morally simple. Stabilizing climate at lower greenhouse concentrations will require a global coordination and restraint unprecedented in human history, while continuing high emissions promises both immediate harms and a persistent, hard-to-reverse reconfiguration of Earth's climate. The epistemic humility this demands is intense. Humanity's lifespans are a sliver. Geological processes are patient. The narrator's vantage, broad, reflective, and clear-eyed, insists that this mismatch of timescales is not a reason for paralysis, but for extended responsibility. Institutional designs that plan on decadal cycles are inadequate to steward a planet whose trajectory now depends on centuries-long chemical legacies. The moral imagination must expand to include stewardship regimes that persist in knowledge and practice across generations. The kinds of institutions, cultural practices, and scientific monitoring systems necessary for such stewardship are not fantasies. They are pragmatic needs. Just as glaciers and loas tell a patient history of the past, so too must societies think in layers, preserving data, maintaining archives, and embedding adaptive capacity into the structures that outlast electoral cycles. There is also room for creative agency. Prediction is not merely a passive activity, it supports intervention. Climate models allow scenario testing. What if emissions halved by 2050? What if negative emissions technologies were deployed at scale? What if coastal defenses are built in regions where sea level will rise? These are practical questions with ethical dimensions. The danger comes not from acting, but from acting without humility and a deep understanding of unintended consequences. Large-scale geoengineering, for example, promises to alter albedo or remove carbon, but it carries risks of regional climate disruption and governance dilemmas. Who decides, on behalf of a planet, to dim the sun or to seed oceans? The documentary voice cautions that technical capability does not obviate the need for deliberative, inclusive governance structures that consider long-term ecological and social impacts. Finally, there is a human feeling that breathes through the whole. The deep time perspective cultivates two complementary emotions: awe at Earth's capacity for transformation and urgency about the fragility of the surface arrangements humans rely upon. To stand, even verbally, at the interface of these timescales is to understand smallness without helplessness. Humanity is a species of vantage and effect, limited in duration, yet mighty enough to push a planetary needle. That paradox is simultaneously humbling and exigent. It asks not for resignation, but for stewardship, ethic, embodied in research, policy, cultural memory, and intergenerational justice. The concluding note must therefore be both reflective and directive. The planet's glaciers, loess, isotopes, and buried coasts are not mere relics. They are the grammar of Earth's story. They remind that warm epochs are temporary breaths, and ice epochs are manifold, patient acts of planetary reorganization. Human agency has entered that long narrative as a new accelerant and as a possible stabilizer. To predict well is not merely to calculate where ice might next gather, it is to locate pathways that minimize harm across scales, to build institutions that extend care across generations, and to accept that the signatures humanity leaves will be read by future geologists as evidence of choice. If there is a final image to carry forward, it is this: a ledger written in silt, carbonate, charcoal, and gas bubbles, in which a species traces a decision. The ledger does not judge, it records. The question the present generation faces is whether the entry will read as an act of stewardship that respected planetary rhythms and minimized suffering, or as a chapter in which short-term gain rewrote the climate in ways that future readers would call precipitous and harmful. To read the past is to be charged by it. The archive is patient. Its testimony is clear. The task now is to make the choices the archive will someday describe with honesty and foresight. What lesson does a planet that has iced itself want to teach those who come after? And will those lessons be heard in time? That single question can act as a fulcrum. It bends the long, patient narrative of Earth into an ethical hinge for the brief and fevered story of human civilization. Ice, after all, is not merely cold. It is pedagogy written in pressure and time. It erases and it archives. It punishes and it prepares. To read the lesson of the ice is to read both the raw mechanics of planetary change and the quieter moral ledger of vulnerability and endurance. The first lesson the ice imparts is about scale. Glaciation is a slow-working force whose effects are colossal precisely because they are patient. Sheets of ice grow over millennia. Their weight depresses continents. Their movement grinds mountains into dust. And their retreat redistributes nutrient-rich sediments that will feed life and civilizations for ages to come. This slow artistry rewrites coastlines, reroutes rivers, and refashions the climate envelope of entire biomes. For organisms tuned to seasons and lifespans that measure time in years or decades, such changes can look sudden and catastrophic. For the planet, they are rhythms, long breaths between which life experiments, collapses, and reconfigures. The second lesson is about paradox. Ice is both destroyer and designer. Where it grinds and buries, it also lays the soils that will sustain crops. Where it scrubs the shallow surface of evidence, it helps create the basins and plains that allow dense human settlement. The Great Lakes are not only a memory of glacial appetite, they are water reservoirs and transport corridors that reshape economies. Lowest drifts born of glacial flour became some of the most fertile lands on Earth. This paradox complicates any moral calculus. The same planetary forces that can erase cultures also create the material conditions for new ones to arise. Third, the ice is a merciless editor of narratives. Structures built on the thin edge of time, wood, textiles, many organics, seldom outlast repeated glaciations. Monumental architecture, city grids, and ephemeral cultural forms can be ground into silt or drowned beneath later seas, leaving chemical traces more likely to persist than forms. Metals corrode, polymers oxidize and fragment, but isotopic anomalies, spikes in trace metals, and long-lived radioisotopes can whisper through sediments for millions of years. The planet thus rewards certain kinds of signals, durable chemistry and geology, while punishing the fragile poetry of ephemeral things. Conceive of memory not as monuments but as molecules and ratios. Those are the archives most likely to survive a planetary reset. Fourth, and perhaps most humbling, is the resilience of life. Microbial mats under ice, photosynthetic refugia and polynyas, chemosynthetic communities beneath kilometers of ice. These are not speculative miracles but observed precedents. Life specializes and persists in niches where energy is scarce and conditions are extreme. The cryogenian, however severe, did not end biological history. It rearranged it. Bottlenecks and selective pressures favored innovations that later set the stage for great evolutionary experiments. The pattern is blunt, crises prune, but they also create the ecological space into which novelty can radiate. Having absorbed these lessons, the inevitable question surfaces with greater weight: could history repeat? And would humanity be ready if the planet swung back toward widespread glaciation? From the vantage of planetary mechanics, the simple, conditional answer is that glaciation is always a possibility within Earth's long orbital choreography. The Milankovitch cycles, the slow changes in eccentricity, axial tilt, and precession, continue to modulate the spatial and seasonal delivery of solar energy. When those orbital configurations favor reduced summer insolation and high northern latitudes, the seeds of ice can find purchase. But the story today is not purely natural. Humanity has become a significant boundary condition on the climatic system. By injecting greenhouse gases into the atmosphere at scale, by altering land cover, and by influencing aerosol balances, humans have changed the amplitude and direction of climate responses to orbital nudges. In practice, the anthropogenic blanket of heat is likely to delay, perhaps by many tens of thousands of years, any natural return to global-scale glaciation that orbital forcing alone might otherwise have produced in the near-term geological future. That delay is both intervention and intervention's consequence. Human action has skewed the probability distribution of future climate states. Yet delay is not the same as elimination of uncertainty. The climate system contains interacting feedbacks and thresholds whose crossing can yield abrupt regional or even hemispheric shifts. Freshwater influxes into the North Atlantic, for instance, can weaken the oceanic conveyor belts and produce rapid regional cooling in places crucial to fertile zones and food production. The lesson is that warming and cooling do not simply cancel each other out in tidy ways. They can generate heterogeneity and surprise. A warmed planet is still capable of producing sudden, disruptive regional anomalies that can dwarf contemporary human capacities for rapid, equitable adaptation. Preparedness, then, demands a dual orientation: stewardship over centuries and resilience over decades. The first axis, stewardship, involves choices that change the statistical envelope of future climate. It means cutting emissions decisively, drawing down atmospheric carbon where feasible, and protecting the biosphere functions that stabilize climate, soils, forests, wetlands, and permafrost landscapes. It also means preserving and archiving knowledge intentionally, robust, distributed data repositories, redundant, intergenerational records of agricultural practice, seed banks, and cultural memory. The ice taught that molecules often outlast monuments. The modern impulse must be to make the best of that fact by ensuring information is preserved in chemically and physically stable contexts. The second axis, resilience, is pragmatic and immediate. Human societies must cultivate systems that can withstand abrupt shifts. Agricultural systems diversified across climate zones, decentralized energy networks that can tolerate supply shocks, water, management infrastructure that combines storage with flexibility, and social safety nets that prevent displacement from cascading into geopolitical collapse. Cities and coastlines can be designed with an eye toward uncertainty, favoring adaptable infrastructure and retreat corridors where necessary. Crucially, resilience is not only technical, it is social. Networks of trust, knowledge transmission, and equitable governance that ensure a crisis does not become a catastrophe for the many. There are specific, tangible actions that follow from these axes and from the ice's lessons. First, protect ecological refugia, places where biodiversity can persist under a range of climates, because they are both repositories of genetic resilience and potential seedbeds for post-crisis recovery. Second, invest radically in monitoring and predictive capacity, satellite systems, sediment coring networks, coastal mapping, and the long-term maintenance of paleoclimate archives. The ability to read short-term perturbations against long-term baselines is not merely scientific curiosity, it is the operational intelligence of survival. Third, secure and diversify food systems with an emphasis on perennial crops, polycultures, and storage techniques that are robust to variation in temperature and precipitation regimes. Fourth, build knowledge repositories in multiple physical and chemical forms, diamond or glass archives, hardened subterranean vaults, and distributed digital platforms with multiple redundancy layers, a modern attempt to ensure that crucial information is not easily erased by geological processes. There is also an ethical dimension that the ice presses upon the present: intergenerational justice. The greenhouse gases accumulated today will persist for centuries to millennia, altering the probabilities and perhaps the very character of future planetary states. Those who inherit the future must be accounted for in the calculus of present decisions. This is not a metaphysical appeal, but a practical constraint. The choices that stabilize climate at lower concentrations preserve a wider range of possible futures and reduce the likelihood of irreversible thresholds being crossed. Acting responsibly means recognizing that the climate ledger records actions long after the actors are gone. Yet the question of repetition cannot be answered purely by mitigation and adaptation. Systemic unpredictability remains. No civilization can guarantee immunity against all planetary reconfigurations. The ice is a teacher of humility. It shows how durable institutions can be undermined by processes that operate on timescales longer than political memory. To prepare adequately, societies need cultural mechanisms that extend stewardship beyond electoral cycles, institutions for intergenerational planning, legal frameworks that codify long-term ecological obligations, and social practices that embed the maintenance of ecological knowledge into daily life and ritual. This is the harder work of readiness, making patience and foresight ordinary. The final caution, and perhaps the deepest lesson, is about legacy. The ice does not judge, it archives. It will record the presence of a technological species not in the triumphal lines of monuments, but in the chemistry of sediments, the unusual ratios of isotopes, the sudden enrichments and deficits of certain elements, and the global synchronous layer that will testify to a brief epoch of intense planetary perturbation. If history repeats in the form of another ice advance, the record of the Anthropocene may be partly erased, partly preserved, mutated into new forms. But the choices made now will determine the texture of that record, whether future geologists read a careful, restrained stewardship or a reckless, wholesale reordering. The ledger will be clear. The interpretation will be left to the patient readers of strata. To imagine the ice returning is to imagine being tested by a teacher older than any single society. The test is not simply whether humanity can survive. History shows life is tenacious, but whether human societies can steward a planet with a time horizon that exceeds immediate political and economic cycles. The ice invites a lesson in temporal humility, that human agency is powerful enough to alter planetary rhythms, but fragile enough that its effects may be remembered long after the intentions of its makers have faded. The planet's final instruction might be distilled to this: treat preservation and precaution as twin imperatives. Guard the chemical signals that are the true archives of civilization, reduce the interventions that would skew planetary trajectories into modes of harm, and build societies whose institutions can hold knowledge and responsibility across centuries. In doing so, humanity does not merely prepare for a hypothetical return of ice. It honors a deeper duty, to be responsible actors within a geological story that will continue with or without any particular species. The question of repetition thus becomes less a wager on probability and more a call to wisdom. The ice, patient and impartial, will continue to write its chapters in silt and crystal. The present chapter, the Anthropocene, will be read. Whether it is read as a footnote of restraint or a loud era of excess will depend not on the inevitability of orbital mechanics, but on choices made now. In that choice lies both danger and a rare opportunity to answer the planet's harsh pedagogy with an ethic of care that can outlast the seasons of any single life.